Tapan Mukerji, sir. Before proceeding further, I would like to apprise about sir. Sir, in the Department of Energy Resources, in the Department of Energy Resources and Geophysics and Geological Sciences, Geophysics and Geological Sciences at Stanford University. Received his bachelor's and master's degree from Banaras University. Geophysics from Banaras University, and his doctorate of philosophy in Geophysics from Stanford University. Geophysics from Stanford University. Also co-authored the rock physics handbook, the rock quantitative seismic interpretation, quantitative seismic information in the earth and value of information in the earth received the publication competition, which received the publication competition decision analysis finalist award from Decision Analysis Society, received best paper award from the Society of best paper award from the Society of and the International Association of Mathematical Geosciences. Machine learning has proven useful for a very large number of application in very large number of application in many part of earth science. Sir is here. Tell us about the sir is here. Tell us about in geosciences and machine advances in geosciences and machine learning. Pitfalls and opportunities. I would like to inform all the participants. I would like to inform all the participants. Brief question and answer session. Brief question and answer session, for which you have to type your question into the chat. You have to type your question into the chat. We will also provide you a feedback form. We will also provide you a feedback form. Our upcoming lectures. We can improve our upcoming lectures. The form will contain that questions. The form will contain two questions related to fill the form. Only participants who will get the form certificate will get the certificate. Also for your pure information, the whole so that we can recorded, so that we can upload it to our YouTube channel. We can upload it now our YouTube channel. We are good to proceed. So now I would like to call sir to take over. I would like to call sir to take over.
Thank you. Thank you for your introduction. Thank you for your introduction. Share my screen and we'll get started. Share my screen and we'll get started. Okay, I hope we can see the screen. Okay, I hope we can see the screen.
Yes.
Are you able to? Yes. Okay. All right.
Yes.
Are you able to? So yes, let's talk about machine learning in geosciences. So let's talk about machine learning in geosciences for quite a while. Machine learning has been around for quite a while in the geosciences, but let's see what is new. So as you mentioned, and we have seen machine learning mentioned, and we have seen machine learning. And when you talk about machine learning, of course, there's artificial intelligence. Then a subset of that is machine learning, and a subset of that is machine learning, and a subset of machine learning particularly has grown very rapidly. So, what are some of the challenges? So, what are some of the challenges for adopting opportunities? These kind of modern machine learning techniques. These kind of modern machine learning techniques for geoscience research. So, what are some of the applications of traditional machine learning? Traditional machine learning, supervised learning, classification, and we have clustering, supervised learning, and we have clustering, linear regressions, those are all various applications of machine learning that have been around many decades, geosciences for many decades. Right, so here's a little bit of history, seismic result. So here's a little bit of history, seismic result acquisition. In the 1980s, that's in the 1980s, 40 years ago, there were empirical regression. 40 years ago, there were empirical regression models. Then later on, there were applications of ANN, artificial neural network, artificial neural network of lithologies and classification of lithologies, Bayesian machine learning for Shelly Sand, sub-resolution Shelly Sand, sub-resolution Shelly Sand, 20 years or so for. And also 20 years or so, deep learning, and also kernel methods. Deep learning, there was kernel methods. That was quite popular at that time, and these have also been applied. And these have also been applied in the geosciences. So, what are some of the algorithms of? So, what are some of the algorithms? There's of course traditional machine learning. There's of course discriminant analysis, very classical discriminant analysis. That has 100 years now. Almost 100 years now, of course, kernel methods, Bayesian classification of artificial neural networks have been around, and then artificial neural networks have been around. Those are also trees and random forests, classification and regression tasks, classification and more currently deep convolutional. And now more currently deep convolutional networks. Deep convolutional networks, they actually have been around for some time. They actually have been around for some time. So if you look at when neural networks started. When neural networks started, Pitts and McCullough in 1943. Pitts and McCullough in 1943, 57, Perceptron, and CNN, Neocognitron, which is the convolutional network, which was there since the mid-1980s. Was there since the mid-1980s. So they have been around for a while. Let's see what is a neural network and what is a CNN. Neural network and what is a CNN. Many of you probably already know this, but let's see. Many of you probably already know this. First, we'll start with a single. So first, we'll start with a single. What is called a perceptron, which is the basic. Or what is called a perceptron, which is the basic. So what this does is, let's say we have some inputs. So what this does is, let's say we have some inputs x1 to x, and so the first neuron it multiplies those inputs by some weight, multiplies those inputs by some weight. So this is just a linear combination of just a linear combination of the inputs, or what is called a bias, or just a constant, right? So what is called a bias, or just a linear, right? So that's a constant. So that's a linear affine function. That's so it takes affine function of the inputs. Very simple, right? So z function of the equals very simple, dot x plus b equals w dot x then plus b. It passes this through some nonlinear function in neural networks. So this nonlinear function in activation function that's called. And so now this could be these, there are various types of nonlinear functions. There are various types of nonlinear functions. This is just a way of creating a nonlinear output y, creating a nonlinear function of the input x, which is a function of the input x. That's the linear plus a constant. That's the linear plus a constant nonlinear function. And we propagate that these days. This nonlinear function. These days, this nonlinear function. The others are also quite very popular, but the others are also quite used. The hyperbolic tangent function, and those are also hyperbolic tangent functions. So this is just a way to build, to systematically build a nonlinear function, to systematically build a nonlinear function of multiple. That's a rectified linear unit. So now instead of having a single neuron, we can have we have multiple neurons coming in, right? So we have x coming in, and layer of multiple neurons, all of those layer of multiply the weights, all of those, and multiply the weights within. Plus, of course, we add a constant term. Plus, of course, we add, and we can have. Instead of just a single layer, instead of just a single layer, multiple neurons, thus multiple of neurons, thus multiple layers of neurons, creates a nonlinear function of the inputs, and nonlinear parameterized base, which is parameterized base. Filing by minimizing this problem by minimizing. Output of the neural network is close to the y that we have in training data. The y that we have in training data. So that's all it is. It's just a way of fitting. All it is. It's a nonlinear function. Way of fitting. It's a systematic way of fitting some nonlinear systematic way of fitting a. So if that y, if that output y is a continuous variable, then it's a nonlinear regression, and we minimize nonlinear regression square error. And we minimize. On the other hand, if y is categorical, on the other hand, if y is categorical, different facies. Let's say we want to predict different facies, oil sands, gas sands, shales, oil sands, gas sands, it's a nonlinear classification problem. So then it's a nonlinear classification problem. Misclassification error. Misclassification error. So that's a multiple layers of neurons. So that's a multiple layers of neurons building nonlinear functions. Just a way of building nonlinear functions. Now, what if these x is not just a single scalar input? Is not just a single scalar input. What if it becomes like a vector like that? Or what if it becomes so now if the x itself is an image? So now if and each neuron is an image. And each neuron now, filter, it could be a convolution filter, 21 by 21 convolution filter that we apply on this convolution filter that we apply. This image can be 2D or also can be an array. 2D or 3D or even higher dimensional arrays of numbers, or even higher dimensional. And we have the arrays of filters. It's just a convolution filter that is just a learn about geophysics signal processing. We learn about geophysics signal processing. Of course, we still have our nonlinear activation function, our nonlinear activation function, tasks, and then there's some additional tasks that is also functions that take place. For example, functions that pool the take place. For example, together, pool the it's called max pooling. Together, can average them called max pooling, and so on. So that's together essentially and so on. So that's essentially a convolutional network. So, like I said, these have been around. Even so, like I said, these have been around. Even this convolutional network is nothing very new. It has been literature and researchers, literature and researchers. So what has changed since the mid 1980s? Why such a big hype? Why such a big hype about convolutional networks? So what has happened is that there's a phase. So what has happened is that the way we do computation in the way we do computing is as a result of multiple and this things as a result of multiple things coming together. So what are some of those things? So one is, of course, the mobile revolution. So one is, of course, the mobile revolution that are growing faster. We have smartphones that are growing faster than the population rate. So lots of smartphone users. So lots of this data is already old. Probably now there are many more. This data is already old. Probably now there are many more. That's a big revolution. So that's a big revolution. Smartphones, they are creating. So smartphones, you can find smartphones even in the remote. You can find smartphones even in the remote villages, even in monasteries. Villages, even in monasteries. So this is creating a lot of data. So this is creating a lot of data. This mobile revolution is creating a lot of every 60 seconds. And for example, every 6 terabytes of data is created. 2 terabytes of data is created. And it is uploaded to the cloud. Pictures, songs, messages, huge data that has come about as a result of the mobile revolution. It has also given rise to global data services, global database services, computational resources, because that data is being uploaded to the cloud, that data is and it's being transferred from one place to the other. You're sending transferred from one place to the other. You're sending sound files and images, sound files, and so on. So there's the cloud paradigm. And millions of cloud businesses now rely on cloud computing. Businesses now rely on cloud computing. Thousands of hours of CPU we can get at a fairly cheap CPU. So that's another fairly cheap big transition. That's another change that has happened since the 1980s. Big change that has happened since the 1980s. We had CNN in the 1980s. We had CNN, but we didn't have this mobile revolution. We didn't have. That's so every 60 seconds, 2 terabytes of data is created, and now businesses, 2 terabytes of data is created, and now businesses, they want to make money advertise and use the data in advertise and use the data in a way to make. That's one part. Money, make profit. Then the other part is the rise. Then the other part is the rise of partly driven by the global, partly driven games market, the global $100 billion industry, and so that has driven the development of very fast, very efficient development of very fast, very efficient. And as a result of that, lots of computing much better than what we could do with CPU, much better than what we could do with CPU. We have a 50x boost in deep learning, 50x boost in deep learning because of the advent of GPUs. You can see that in the GPU versus on the left. GPU games, gaming industry has given rise to gaming industry has given rise to GPUs, and that has helped for good GPUs, and that has helped machine learning speed. And then there has been development of frameworks. Such as TensorFlow, PyTorch, frameworks such as TensorFlow, PyTorch. And this allows scientists, not computer scientists, but other scientists like geoscientists, but this allows us to use deep learning without having to develop everything without having to develop. If you were a geoscientist in the 1980s, if you were a geoscientist in the 1980s, and if you wanted to use CNN or you didn't have TensorFlow, you would have to write your own code from scratch. You would have to write your own code from scratch, and that would now, because we have this frameworks readily available, we don't have to be computer scientists, geoscientists, we don't have to be computer scientists, we can take those frameworks and start developing our. And these deep learning models have now begun human performance in many computer graphics applications, where we see that human performance, we see that classifying images performance in classifying images 5 to 10% error. That's around in 5 to 10% error. Deep learning networks like the RECENY, deep learning networks like the RECENY outperformed that human performance. Also, we see other kind of machine learning, deep networks, other kind of machine learning, deep networks, plus other advanced research methods, machines to beat humans in machines games like Go, AlphaGo, and chess games like Go is supposed to be a game that is Go is supposed to be a game that is complex and chess. Many more times complex than chess. I don't know the game itself, but how that's part of AlphaGo, how that they defeated the world, the human champ defeated the world human chance. Now, artificial intelligence, machine learning, deep learning has become a big business. Machine learning, deep learning has become a big business. So there's a huge value of deep learning. So McKinsey reports that there's a all that is good. So what does this mean for all that is good? So what does this mean for geoscience research? Because of all of these things coming together, because of all of these things coming together, because of phase transition, science, computation, the way we do scientific research, computation, the way we do scientific research, computation research is phase transition. It has changed. There has been a phase conventional approach would be to invert a model. Approach would be have some data, invert. We have some data using some physics. We create an earth model, using some physics. We create an earth model, and then based on that earth model, we make some predictions. And it's challenging because inversion is non-unique. And it's challenging because inversion is non-unique. And then from the model, we have to make predictions. So, for example, we might have seismic data. So, for example, we might have seismic data to create a model of not only the impedance, model of impedance, the impedance, but phase impedance, porosity. We have to go to phase, and then once we have that earth model, and so on, and then we have forward simulate the flow. Then we forward simulate the flow. And we want to make some predictions about the and we want to make some predictions about the so we have data, flow behavior in the future. So we have data, we have something that M predict, and we have H something that, for example, might be the flow behavior. For example, oil and gas flow behavior, or oil and gas reservoir, interested in flow of contaminants in a groundwater reservoir, flow of contaminants in a groundwater containment of CO2 or in the subsurface, containment of CO2 in the subsurface. So that's a prediction. Conventional approach, you go from data. Conventional inversion, very challenging data. We do the inversion, very challenging problem. We go to the model, and from the model. But now with the machine learning approach, what we can do is we can flip the arrows. What we can do is we can flip the arrows around, and we can start from the model and Monte Carlo simulate. We can create a Monte Carlo simulate number of data, create a large number of data from that model, and a large number of predictions from that model. Much easier. There's no non-uniqueness there. Much easier. There's no non-uniqueness there. No ambiguity. And once we have physics, training data set, and once we have a training data set of D and learning model to, then we can use learn the relation between D and H. Learn the relation between D and H. So there's no explicit inversion. We relation between H and D, and then of course when we have and D. And then, of course, when we have particular D observed, specific, we can use particular D machine learning model. Then we can use predict H for that model to predict H for that different way of. So that's a different way of doing prediction modeling these days without having to do explicit inversion, without having to do explicit. So, but of course, there's a greater emphasis on the prior. But of course, there's a greater emphasis on the prior model. So, what are some of the opportunities and challenge? So, what are some of the opportunities and challenge? Training data. So, machine learning requires training. In particular, deep learning requires a lot of. And in particular, deep learning requires a lot of. We do not have. We of course have a lot of data in geophysics. But we do not have a lot of labeled data. But we do not have a lot of labeled data. So unlike computer graphics, and computer graphics, unlike computer graphics, images, computer graphics, we have many images, and you know the labels. So we have cats, and you know the labels. So we have cats, and then you can train the network with this labeled set, and then you can train the network with this labeled set, and then will be able to predict for new images. Will be able to predict for new images. So, for example, in computer graphics, and business applications, that's a labeled data set. That's 14 labeled data set. It has labeled images. 14 million image has a labeled images. And so that's nice. We can use that to train. That's nice. We can use that. If we don't have those kind of labeled data sets, if we don't have those kind of labeled data sets, well logs at every size and trace. Well logs at every size and trace. We would not have well logs at every size and trace. We would not. So what we need is domain knowledge. So what we need is domain knowledge to augment some training data, but we need to augment some training data, but by using domain knowledge, by using physics, by using domain knowledge, combined with statistics. So pure machine learning combined with statistics. Pure machine learning is we combine that with data driven. Domain knowledge combine that with physics and geology. Domain knowledge. So when we take advantage of both of them together, when we take advantage of both of them together, predictions, then we can better predictions. We can make better decisions. Better predictions. We can make better decisions. All right, so now let's look at some examples. Guided deep convolution networks for seismic deep convolution networks for seismic reservoir phases estimation from seismic data, reservoir phases estimation from seismic data, and then geobody interpretation using, and then geobody interpretation using deep net, UNet, which is another kind of deep network. So we have seismic impedance. What we want to know. We have seismic impedance. What we want to know. We have seismic deep network. We want to use CNN, a deep network. To predict, so that's impedance inversion, but not in the usual traditional sense of impedance inversion. usual way of doing it. That was using machine learning. Usual way of doing it. Open up using machine learning. It's no longer a black box. Open up this box. So it's like I said, it is relatively easy to build a neural network and predict on the build a neural network data set and predict. But what are some of the questions? How good is a network? But what are some of the questions? Generalization network. Can it generalize? Generalization to types of data that it has not seen. To types of data. So can it extrapolate for unseen scenarios? So can it extrapolate for unseen scenarios and uncertainty? So of course, again, like I said. There have been many applications of neural networks in artificial neural networks, and some examples are given here, non-exhaustive. And some examples are given here, non-exhaustive. And those have been around, like I said, from the 1980s. They have been used for inversion of seismic data. They have been used for inversion of seismic data for elastic attributes, lithology and permeability prediction from well logs, lithology and permeability prediction from well logs, and also for full waveform inversion. That's more recent. So let's see how we do it. So we have to use synthetic modeling. We have to use synthetic modeling to generate the label training data set because we don't have the label training data set, fully labeled training data set. Then of course there's building the neural network architecture. Then of course there's building the neural network architecture, and then systematically testing the performance of the network and the generalization capability of the network and the generalization capability of the network. So let's go through the workflow. So how do we generate the label data set? So how do we generate the label data set? So that means we need to have pairs of many pairs of impedance and the seismic trace corresponding seismic trace. And that's a label data set. So to generate the label data set, we have to start with the geology first. We have to start with the geology first. Idea of the geology, the facies, in this case, idea of the geology, how they're distributed vertically, how they're distributed vertically. We have to have a model for that. Spatial correlation. So we have to have a model for that. Then for those different facies, we have to assign their porosity. We have to assign their porosity, the different porosity, clay content. From that, we put those into rock physics model, which will give us those elastic physics model, which will give us the elastic parameters. From VP and density, we can get the impedance. From VP and density, we can get the impedance. And once we have the impedance, we can compute the size. Wave propagation to compute the size. For the geological part, we use what is called indicator simulation. We could also use indicator simulation, Markov models. We could also use other kind of that geology models to accounts for the spatial correlation between the facies. Accounts for the spatial correlation between the facies. We have to populate that with porosity and we have to populate that with porosity. There again we use clay content. There again we use Gaussian simulation method called sequential Gaussian simulation. Then those things are used as input into a rock physics model. And then rock physics model gives us the impedance. And then rock physics model gives us full waveform seismogram modeling that gives full waveform seismogram modeling. So now we have this pairs of impedance. So now we have this pairs of impedance and seismic. Of course, with our label data set for many thousands of do this realization. Many thousands of. So we have 2,000. And this is divided into a training set. Validation divided into training sets. A validation set and a test set. Nothing hard and fast about that, but those are nothing hard and fast about that, but those are. And then there is the training, right? So there will be the input. And then there is the training, right? So there will be the input architecture. The output is the known impedance. The output is the known impedance. And then input and output, the weights will be optimized. The weights will be optimized such that the neural network gives us the training phase. And then once it is trained in the prediction phase, and then once it is trained in the prediction phase, we'll have a new seismogram. Output will be a predicted. Output will be a predicted impedance trace. So then we train them on different example, and then we train them on different example, and then after test training, we see how it performs. Test. So here we have how it performs, which the neural network has not seen before, which the neural network has not seen before. And you can see the red is true, and we can see the CNN impedance, and you can see the CNN. Predictions dotted line, and it does a pretty good job of capturing, and it does a pretty good job of capturing the distribution of. We can also get the posterior distribution, uncertainty around the posterior distribution, uncertainty around that Bayesian computation using and so there we have the blue band, and so there we have the blue band estimate that gives us some estimate of perform when we have a challenge data set. When we have, in other words, challenge data set. In other words, where it has not seen that kind of data. So, for example, let's say that we have a rock physics model, and we use that we have a rock physics model, and we used regular testing in training. We use regular testing in training parameters, which are given as parameters, which are 11 as 13, 14, and so forth. Some parameters, 13, 14, and so forth. Some parameters, what those parameters are. But now in the challenge test, so CT is a challenge test, RT is a challenge test. Now we're using some rock physics parameters that using some rock physics parameters that 6, 7, 8, 9. It has not seen before. And similarly, maybe during the training and during regular testing, training and regular testing, we have wavelet which has a certain range of seismic wavelet which has a certain range of frequency that you see there, 30 to while for the challenge testing we while for the challenge testing when it has a frequency that it has not seen when it has a frequency that it has not seen before outside that training range. Rock physics models, wavelet phase, wavelet models, wavelet phase, wavelet frequency. So let's see how it performs. Now, of course, it will perform. It doesn't perform as well as the regular testing. Perform as well as the regular testing. Deviate a little bit. You can see now it true is again in red. A little bit. Prediction true is again in red. And so there are some more mismatched than the regular testing. More mismatched than in the regular testing because it has not seen those because it has not seen those before. So then we can see what is the error for the different scenarios. What is the error for the different scenarios? Which ones are the most sensitive? We're plotting error. So here we on the y-axis plotting error. It is just on the y-axis, so absolute error. It is just and here we're plotting absolute error. The different scenarios. So let's say the different scenarios. So let's say the rock physics parameter. So CT is the rock physics parameter. Challenge testing and RT is a challenge testing and RT is a regular testing. So with regular testing we have some errors here. So with regular testing we have some errors here, of course. But you can see now if the rock physics model is not correct, if the rock physics model is not correct, then the error increases. Not seen. Similarly, then the error increases. The wavelet we have to have a good constraint. We have to have a good. You can see the frequency of the wavelet. You can see the frequency of the wavelet. If we have the regular testing already seen, if we have the wavelet that is again we have errors around 10, 12%. Again we have errors around 10. But if we have a wavelet that is quite different, but if we have a wavelet that is quite different, so then the error means the rock physics model parameters. That means the rock goes model parameters. Physics modeling goes into the physics modeling, those are important, the rock physics and so forth. And of course, there's application to field data. So of course, there's application to field data. So this was applied made available by Equinor, made available by Equinor. And so these are some applications of the CNN-based seismic applications of the CNN-based seismic impedance inversion. All right, so that's how we test the generalization, that's how we and see where the network generalization and see where the network will extrapolate for unseen scenarios and how it will extrapolate for unseen scenarios. Now, that was an example of a supervised learning. That was an example of a supervised learning. But we can also do this in a and what we do here is that we have the input seismic trace. We have the input seismic trace, right? We have the CNNs, and then we have the end outcomes, and then the impedance or VPVS density, an impedance. But now we don't have any labeled pairs of data. But now we don't have any labeled pairs of data. But what we do is during training, we take this during training. So this is we take this called a latent space. So this is now called a latent space. The latent space of the network. And we take that output, we compute the reflection coefficients, we compute the reflection coefficients, output seismic gather, and now we have an output seismic input seismic gather, and the loss function now is the difference, and the loss function now is the difference and the input between the computed seismic gather and the input. Once this is minimized, then once this is minimized during the training and during the prediction phase, we take away the prediction phase. This we take away the convolution, and this self is the output, the latent space. So this is nice because now we do not need to have labeled. Nice because now we do not need to have labeled with a data set seismic gather. We can just work directly without having seismic gather directly without having. So we can do the supervised, we can do unsupervised. So we can do the supervised. The predictions are comparable, both of them. The predictions are comparable, both of them are able to predict quite nicely. Here are some comparisons. Here are some for the supervised case, we require a labeled data set. Supervised case, we require a labeled data set. And supervised, we do not require the wavelet. But more importantly, we require a low frequency background mode. A low frequency background need for the supervised case because we do not need for the supervised case because you already have. The supervised learning is faster convergence. The supervised learning is faster convergence. Unsupervised in our example. The unsupervised was a little bit slower. All right, so that's an example of impedance inversion. So that's an example of impedance inversion. But of course, impedance by itself is not. Of course, impedance by itself, you cannot just take high impedance and predicting. You cannot go to the market and sell impedance. What we really need to know is how the reservoir need to know is how the reservoir will produce it. What so that come out of it go produce to the phase sheets. So that means you have to go where are the sands, where are the shapes, reservoir phases, where are the sands. Study is about reservoir phases. This next study is about semantic segmentation using semantic segmentation using again deep networks, deep convolutional networks. So here's our workflow, right? So here's our workflow, right? So we have to have some prior information about geolocation, and we want some uncertain quantification, and we want going to samples from the posterior distribution of reservoir facies from the posterior distribution of reservoir facies data. Given we have to do it in an efficient manner. And of course, these distributions are high dimension, very high distributions are high dimension, very high dimension. We have the Bayesian approach. We have a prior. We have the Bayesian of the prior distribution of all facies models for that all facies models, and for that geology high dimension, not just a univariate, of course, high dimension, not just. Then we have the likelihood. Then we have the likelihood given that likelihood of the data, and then we have the posterior and we want samples, and then we have the posterior and we want samples from the posterior. Since these distributions are so high dimension, since these distributions are so high dimension, write down those distributions, explicitly write down those distributions. Do only is to sample. And what we can get realization is to sample the prior realization by the likelihood, and the prior realization by the likelihood, and then how do we do that? Realizations. Again, now we are going to do it using machine learning. Again, now we are going to do it using machine learning instead of doing this inversion. We'll not do the inversion from sizing data to elastic properties and elastic data to elastic properties and elastic properties to the facies. Monte Carlo simulation just from the geology to sizing data and from the geology to sizing data and create a training data set, and then which will then be used to train, which will then be used to train the. So we'll define the prior on the target. So we'll define the prior on the target from the prior to generate multiple sample from the prior to generate multiple from that facies model. We have to go to rock from that facies model. We have to simulate the physics and wave propagation. Then we will learn the relation between the H and D. Then we will learn the relation between the H and D. We can then predict directly the facies for a given predict directly the facies for a given D observed. So that's our workflow. So that here in this case we use a different geostatistical method called multiple point realizations from the prior. The realizations channelized environment. So we have some background of channelized environment. So we have some channels of different thicknesses and widths, channels of different and the channels of different fluids. Some of them are all saturated fluids. Some of them are brine saturated. Some of them are all saturated. Some of them are brine saturated. So we create multiple realizations. So we create multiple realizations. So that's a geology. Multiple point. Then we have rock physics models that use. Then we have rock physics models that use the VPN density. And then we have the forward seismic model. And then we have the forward full waveform normal incidence seismogram, which is full waveform normal incidence seismogram with a 35. So that gives us seismic data. And so now we will train the. So now we will train the deep learn the relation between the seismic data, learn the relation between the seismic data and the corresponding. So this will be our deep convolutional network. So this will be our deep convolutional network, the semantic segmentation. And so here, other details we use what is called dilation. Other details we use what is called dilation, such that it convolution exponentially increases the field of view. Exponentially, so in that way we can have a larger field of view without increasing the number of without increasing the number of filters. The original filter, then we step it out. Original filter, then we step it out by steps of one. So we still have 9 filter coefficients, but we still have 9 filter coefficients. So that is a larger field of view. So that is. Then of course there is a training. Then of course there is a train that we optimize the parameters. So train that we optimize the parameters. So it is trained on 5 hours and. And about 5 hours. We have the training set error. So we have the training performance set error, 94% performance. That's pretty good validation. That's 92. So that's on the test set. That's 92. So that's we can also see what it has learned. We can actually also see what it has learned. We can actually go into the layers and we can look at the different where it has layers, where it is activated, where it has. So we can see, for example, in a particular layer, layer number 7, the third slice, layer is activated actually by the. It is activated actually by the red facies here, the oil sands. What is red facies here, the oil sands. That's what is activating this layer over here. So we have to, of course, evaluate if the model is overfitting. We have to, of course, evaluate if the model is overfitting. Very high accuracy training set. But very high accuracy training set. If it is poor on the test set, that means it is overfitting. Poor on the test set, that means it is overfitting. We can also see what is the. We can also see. What is the bound on the accuracy with the Bayesian classification on the accuracy with true impedance with the perfect impedance? With true impedance with the Bayes error, the best that anybody Bayes error, the best that anybody could perform. Any algorithm we have synthetic data. In this case, we have synthetic. So the upper bound, right? This is the Bayes. So the upper bound error. This is the Bayes with the true impedance, perfect impedance. With the true impedance, exactly perfect impedance. If we knew the impedance exactly, the shales. So here we have higher impedance. So here we have the brine sand, middle impedance, then we have the brine sand, middle impedance, and then we have the oil sand. So if we knew the true impedances, the limit would be 97. The upper limit would be 97. Method could be able to best any method could be able to do. How does the CNN compare to that? How does the CNN compare to that machine learning? How does the traditional machine learning algorithm? So if we can just So if you can just standard classification with seismic impedance, with the low resolution seismic impedance, with the low resolution, how does that perform? So this is, we can call this traditional perform. So this is, we can call this traditional Bayesian classification, machine learning. Bayesian classification, we see that the classification accuracy is 82%. Compare that accuracy is 87%. Compare that to traditional machine learning or traditional Bayesian classification. Traditional machine learning or traditional Bayesian classification lower accuracy of 82%. Lower how does the CNN do? Well, if you look at the CNN, how does the CNN do? You see that if you look at the CNN, gain in accuracy. You see that there's a big gain in accuracy. Traditional machine learning 82% compared with traditional machine learning, and the upper bound is 97%. And the upper bound is 97%. Look at the computation time. Bayesian classification is very simple. Bayesian training and prediction, everything takes barely training and prediction, everything takes barely 2 minutes. So it's very easy. Compared to that, the convolutional network. Compared to that, set up the convolutional network. Training time. You have to set up the network. Hyperparameter tuning. So that will take hours. Hyperparameter tuning. So that creating the data itself will take some time. Creating the once it is trained again, the prediction time is quite once it is trained again, the prediction time is after the training you get a big jump. After the training you get a big jump in accuracy. You get a 10% improvement in accuracy. Go on to, and of course that improvement in your go on predictions and improvement in your predictions. And of course that can be applied. And then a field application. So this is and the field application. So this is an offshore system. This is a turbidite system, and then you can see how it's a turbidite system, and then you can see how convolutional network is predicting the different convolutional network is predicting the different channel faces. So below this channels, and we have table contact. Below this all the water contact. Table contact. We have the all water contact. Brine sands. Below that in red, you have the brine sands. Above that in red, you have the oil. We can also use machine learning for geobody interpretation. And here's an example. This is a nice example of interpreting the channels and so forth using a different kind of network. This is using a different kind of network. So we have the input image. And so we have the input image is encoded that is down collapsed. It is encoded down into sort of latent vector, then it is decoded back latent vector, then it is decoded back into an output segmentation links. Of course, there are these across the links, encoding and decoding parts. So that's a unit encoding and decoding parts very well, and that's an example that also performs very well. And of course, then you can see that. And of course, again, training takes time. Of course, again, training takes time. But what about human experts? So, what about training a human expert to do this? What about training a human expert to do this interpretation? So that also takes time. They have to go through human being at least a master's level course in at least a master's level course in geology. So that's 2 years of master's geology. So that's 2 years of master's work, and then they have to learn how to interpret data until they become learn how to interpret data until they become experts. So that also itself is a few years of human expert also required training. So human expert also required training. Now, what about performance? Very highly skilled. Now, it might be true that a very highly skilled might be able to perform better than the CNN. Might be able to perform better than the CNN. But remember that that's true. The human interpreter would take much longer. Human interpreter would take much longer to interpret such while the whole cube machine learning. While network once it's trained, it predicts the whole cube. Once it's trained, it predicts the whole cube. It does the interpretation in a fraction of a second. So that's another thing. It's much faster. Thousands of times faster than the human. Thousands of times faster than the human. And then the other thing is error consistency. And then the other thing is so let's say that a human expert performs at 95% level, performs at 95% level. Deep learning network performs at maybe 92%. Deep learning network performs at less than 92%. But what happens is when the human interpreter is working on the size, when the human interpreter is working morning when they're fresh, they might be more accurate. When they're fresh, they might be more accurate. After seeing many lines and after seeing many lines and the error rate changes. So the error rate doesn't stay consistent. So the error rate doesn't stay consistent. They become tired. Sometimes it's more, sometimes it's less. They become tired. It is consistent error. It's the same overall. You can consistent error. It's the same for overall. You can keep it. You can keep on running the whole cube. The error is consistent. Go through the whole cube. The error is pros and cons, and understanding that both pros and cons, and be very useful. We can use. Be very useful. We can use the machine to do the tedious work with a consistent. We can use the machine to do the tedious work with a consistent. And the human experts can really focus on the challenges. Human experts can really focus on the challenges where and let the machine requires human expertise. And let the machine. So phase transition in the computation machine learning. This is an opportunity. Computation machine learning. This is an opportunity. It was not years ago. We could not do this. 20, 30 years ago, we could not coming together because of all the mobile revolution, cloud computing, mobile revolution, and the computing, GPUs. Now we have different ways of doing things. Now we have different ways of doing things. Machine learning is not a black box. We can learn. Machine learning is not a black box. We can learn the machine. We should be able to take advantage of this transition in our research and also for the industry in the research and also for the industry. Of course, there are pitfalls. There are challenges. There are pitfalls. There are challenges. Our training set is important. Our training set is important. If it is biased in some ways, that might have heard of the Google flu, might have heard of the machine learner scientists. They tried to machine learner scientists. This was before the pandemic. It was not the COVID. This was before the pandemic. It was not the COVID flu. It was more just the usual flu that comes in the winter. Just the usual flu that comes in the winter. Because the training set was not correct. But because the training set was not correct, it was biased. Clicks. They were just looking at Google search clicks, which was not really related to the people who actually had not really related to the people who actually had the flu. So they completely mispredicted progress of the flu, and these are all progress of the flu. Highly these are all machine learning people. So you have to be aware of machine learning people. What kind of training data you have? What kind of training data you have? What if training data does not have the right rock physics? If your training data does not have the right physics model, or if it does not have the right Bayes challenge, right? That might will not be so good. So you have to make sure your training is so good. So you have to make sure your training all of the different scenarios that you might expect. All of the different scenarios that you might expect to see when you go. So if you can meet those challenges and avoid, if you can meet those challenges and avoid those benefit from the opportunity this provides us, benefit from the opportunity geoscientific research in a new way, geoscientific research in a new way, in a different. Of course, we need domain learning to augment machine learning. Domain learning to augment machine learning. Graphics where we can field of computer graphics where we can data label data, get lots of data label. For example, when people want to train machines to drive a car, machines to autonomous drive a car, they can actually autonomous vehicles camera. They can actually put driven by a human person, and they can go on driven by a human person, and they can go on thousands of kilometers of driving kilometers of driving and so forth. So they have lots of camera and go and collect. So they have lots of data, and they have the labels, but we do not have and they have the labels, but we do not have always. We have a lot of data, but not understand the geology and the physics, understand the geology and the physics together with the machine learning predictions, and better predictions will ultimately lead to better decisions. All right, so I will stop there, and I'll see if I can answer any questions.
Thank you very much, sir. Sir, we are very grateful to you for delivering such an informative lecture. Our participants' question, if there is.
So where's my meeting? Okay. All right. So where's the chat box? Okay, I think somebody. All right, let's see. For machine learning is a strong. Grasp because you have to use some grasp. Right? Like I said, there are all these. You have to use some frameworks, right? Like that are already out there, so you do frameworks that are already out there, so you do not have to go to the C++ level of programming everything. But you have to have level of programming everything. But you have to have something at the level of those levels. So you have to have Python, the machine learning level. So you have to have a lot of programming. So you need to have a lot of reasonably good grasp of programming. If you want to do machine learning.
Sir, good morning, sir. Sir, my name is Banaras, sir. I wanted to ask the question.
Go ahead.
When we have.
Go ahead.
When I have a question, sir. Yes, sir. When we have more models that will be predicted with the help of machine learning, how to confirm that this is what we have more data sets, because there is a possibility more data sets. So machine there is a possibility always that giving me more results like models. I'm giving me more results like models.
No, machine will not take giving you more results. No, machine will not take the machine will be giving you more results. What do you mean the machine will be giving you more results? You have to define what's the input. Of course, you have more data, but then you have to do that. Have more data, but training, validation, and testing. Training, validation, and testing. Right. So that's how whether the machine is being trained, whether the machine is not overfitting correctly and not overfitting well on the test set. So performing well on the test set. The whole process is very well defined, right? So you have the whole process is very well defined, right? So you have overall data set, divide your training overall data set, a validation set, training set, test set, a validation set, typically 70, 15, 15, but typically 70, 15, 15, but it could be, some other proportions.
And when we have such kind of data sets, I mean, so can we correlate with the codes that we are obtaining?
Well, so then you have to create a data set, right? Well, so then you have to create a data set, right? If you do not have enough data, then you have to augment it. Do not have using the physics, then you have to augment it, right? Using the physics. Like so, first you have to define what is your problem. What is the input? So first you have to define what is your problem. What is the input? What is the output? And from what you're trying to predict, right? So what will be your from what you're trying to predict, and what is the what will be your input? Define that, and what is then you have to make sure that you have a good training set. Then you have to make sure that your original data is not enough. Then if your original data is not enough, then you have to augment it. Geology using rock physics or other domain knowledge and rock physics or other domain knowledge. Good training, and then you have to once you have good training, divide it data set, then training, divide it in test, training, and go through and look at the metrics, the performance, and go through and look at the metrics, the performance metrics, and see whether it is performing okay or not.
Sir, one more question, sir. How do you all do? Sir, one more question, sir. How do you all do which is not even correct and different kind of channel or different kind of channel that may be around the
yeah. So that's right. Yeah. So that first have to define your prior. You first have to do what is called prior falsification. So you have to do what is called prior falsification. Build a model that you build a model that is only fluvial environments. But your seismic data that you have actually comes from a turbidite data that you have actually comes from a turbidite. Before you do that, then first you start training your machine learning model. Before you start training your machine learning model, prior falsification, you have to see prior falsification. You have to fluvial environment models you're building. Can fluvial environment models you're building? Can is it even statistically consistent? Is it even consistent statistically? So you'll see that the seismic data is coming from. So you'll see that if your seismic data is build all your models environment based on and you build all your models from, you'll see that that model is not statistically consistent with the seismic data that you have. Statistically consistent. So then you put the seismic data that prior model, and then you start throw away that prior model, and you have to start fresh with a new prior model. There's a question there from Vishal Pandey. From Vishal Pandey. I have to look at the other chat questions, right? Look at chat questions, right? So for training the machine, we generally use synthetic data. For training the machine, we generally use synthetic data. You only use synthetic data if you do not have real data. Use synthetic data if you do not have real data. You always use real data for training. If you have real data, you always use real data for training. It is not correct to say that we generally use synthetic data. To say that we generally use synthetic data. Generally use real data. Generally use, but our problem is real data. In Geosciences, we do not have labeled Geosciences. We do not have labeled. We don't have enough data. We do not have enough. We don't have enough. So we have enough labeled real trace. So we have a wherever we have a well, we have the impedance. Wherever we have a well, we have the impedance. How many wells do you have? Maybe you have 10 wells. How many wells do you have? Maybe even 100 wells. Maybe 20. That's only 100 pairs of seismic trace. That's only 100 pairs of seismic trace impedance, right? So you always use real data, but then you always use real data, but then when that real data is not real data, by using synthetic data. The real data by using synthetic data.
Sir,
go ahead.
Sir. Yes, sir. Good morning. Sir, actually, my question is like you mentioned that. Sir, actually, my question is like you mentioned that, like in the research with you, Dr. You mentioned that you generated the model. You mentioned that you generated the model space of patient deep posterior using deep learning. Did I understand that like correctly? I mean, did I understand that like correctly? I mean, for some research into that particular research into that particular direction.
Yeah, you understood correctly. The models that are selected afterwards, realizations, at least approximate realizations, at least approximately from the correct Bayesian posterior.
Yes, sir. Like yes, sir. To understand like the processing, to understand that particular direction, the processing, like what should I look into? Like what should I look into?
You should read the current papers, right? You should read the journals like Geophysics, right? You should read the journals like Geophysics, Computation, Geosciences. Read those Computation, Geosciences. Read those, and then also read the fundamental basic books. And then also read the fundamental basic. Have that background, or in machine learning, you don't have that background, or Coursera, for example. Andrew Ng has a course, for example. Andrew Ng has in that course, right? I hope all of you have taken that course, right?
Sorry for interpreting, sir. Actually, sorry for interpreting. I wanted to like. I wanted to ask is like how did we generated the posterior? How did we generated the posterior? So it is a multi-dimensional. It is not just so it is a multi-dimensional. It is not just a single parameter.
High dimensional, right? That's correct. So it's high dimensional from the posterior. So you sample from the because you have the prior because you have the prior realizations, right? You have those. The machine learning, the network learning, machine learning, the network learns the relation between all of the prior generated data, right? So prior generated data, observed data. So now when you have an observed data, predict which ones are the prior realizations, right? We'll see which prior realizations, and see which. So then you get the posterior from that. Right? So then you get the posterior from that. Select what is called get a posterior by select what is called approximate Bayesian. So you have approximate Bayesian computation. Right? So you have where you look at the errors, right? Which ones are the samples errors closer to the observation samples which are closer to the observation. So first, before you have an observation, so first create the prior. Right? You have the model and you have the data. Create the prior. Right? You have the model and you have the predictions, which is the H. So the model H and D. You have a set, which is the H. So H and D. You have a set. You have whatever. 2000, created the prior, and then you have created the prior, and then you have understand learning, which captures the statistical relation between captures the statistical relation between and the prior H. Prior generated D. Once you have trained that, now you have an observed. Once you have trained that, now you have an observed D. So now you can say, okay, observe. Put that into the okay, now machine learning. Put that into the machine learning. Which ones are close to it, and you can see so you do which ones are close to it, Bayesian computation. What is called so those will then give you the posterior realization. So those will then give you the posterior realizations.
From what I understand, you generated prior samples, a list of prior samples using the convolutional neural networks using the convolutional neural networks you generate the posterior.
No, the posterior distribution is for a given observed data, right? So for a given observed data, right? So the prior and we have the prior data. We also have the prior data. And we have the prior data. We also have the prior data. 1,000 sets of data D, which is high dimensional, right? So data D, which is high dimensional, and we have 1,000 facial models. And we have 1,000 facial models. It's a section, section, right? So we have this pairs in the machine learning. We have this pairs learns the relation between CNN, high dimensional learns the relation between now the high dimensional observed. So now when we have an observed what the corresponding facial, then it can predict what the corresponding facial is.
Answer one more question, sir, please. Answer one more question, sir, please. Full waveform technique did you use for?
So in that case, I used Kennett's method. So in that case, I used Kennett's method. Or Kennett's invariant embedding method. So that's invariant embedding method. So that's
reflectivity, as in like which Dr. Minalsan, as in like which Dr. Minalsan uses.
Same, yeah. Same.
Thank you, sir.
Right. But thank you, sir. But reflectivity method is in the time domain. Reflectivity method is in the time domain, and Kennett's invariant embedding method is in the Fourier domain.
Thank you. Okay, sir. Thank you.
Okay, what other questions? Okay, what advice on how we just start building a fundamentals of ML? So yeah, so like I said, fundamentals of ML. Look at some basic text. There are some tutorial papers that comes out. There are some in the leading edge, for example. That comes out in the leading edge, for example. Those are just to get started because they don't. Those are just to get started because they don't. But they're also good books. But they're also you can look at good books. If you have no background in machine learning, then you can start learning background in machine learning. Traditional machine learning, don't have to traditional machine learning right away. Don't have to dive into traditional learning right away, but you can start. And for that, there are many courses on Coursera. For that, there are many courses on Coursera. Right? If you don't want the certificate, those courses are free. If you don't want just listen to those courses, so you can just the Coursera course that I mentioned is the course. The Coursera course that I mentioned is the course by he was a professor at Stanford University. Now he was a professor at Stanford University. Now very famous company advisor. Famous is an advisor to Google. Artificial intelligence coming. So Andrew artificial intelligence coming. So Andrew right? So that's the name. And you can find his course. And you can find his Coursera Andrew Ng on Coursera Andrew Ng. So that course definitely that's a basic. So that course definitely that's a basic. How to avoid learning. It teaches you how to avoid validation. How to do testing, validation testing, how to do training and validation testing, how to do that. Get started if you have no background. To get started if you have no background. Other question is if one wants a career in geoscience, if one wants a career in geoscience, what learning or machine ferret learning or ferret? What typo there? I don't understand. Typo there? I don't understand. What should you prefer, machine learning or ferret? What should you prefer, machine learning or ferret? I don't understand the question. I don't understand the question. Okay. Any other questions? Any other
Hello,
questions?
sir. I am Deep Kumar Singha. Hello, sir. I am Deep
Yeah.
Kumar Singha.
Yes.
Yeah, I am. Hello, I
Yeah.
am Deep Kumar Singha from
Yes.
Department of Geophysics. I am Deep Kumar Singha
Yeah.
from Department of Geophysics. Question.
Yeah.
I want to ask can machine learning predict poor pressure for sand or limestone lithology? Sand or limestone
It
lithology?
depends on your training set.
It
Right, in
depends on your
machine
training
learning,
set.
the main thing is the training
Right,
set.
in
Do
machine
you have a
learning,
good
the main
training
thing is
set?
the training set.
Do you have a good training
Okay.
set?
So if we have a training data set, if we have a can it follow the basic theories that can it follow the basic theories that that effective stress what do you know that increases effective stress the porosity increases linear the porosity okay linear that's why the existing that's why the existing equations are about model like equations are about power equations are able to predict logic cell pressure for but cell logic cell go for sand or limestone go for sand or limestone if you have a testing data set and if you have a testing data set to predict and if you are able to predict sand on limestone using machine learning methods limestone using machine learning methods theory so could it follow the basic
Well, it is
theories
purely data driven, right? So
Well, it is purely
machine
data
learning
driven, right? So
doesn't have
machine
any
learning
physics. The
doesn't
physics is
have
already
any
in the training data.
physics.
It
The
is
physics is
implicit
already
in
in
the
the
training
training
data.
data.
It
So
is implicit in
machine
the
learning
training
is
data.
just a
So
statistical
machine
relation
learning is
between
just a
the
statistical
input and
relation
the output that
between
you have in your training
the
data.
input and the
So
output
machine
that you
learning
have
is
in your
not going
training
to
data.
predict the theory.
So machine learning
If
is
you have
not
a
going
good
to
training
predict the
data,
theory. It will
if
be
you have a
able to
good
learn
training
that
data,
relation, and
it
then
will be
for a
able to
new
learn that
new
relation,
data
and
where
then
you not
for a
have
new
the new
core
data
pressure
where
to be
you
able
not
to
have
predict.
the
So
core
that's
pressure
all
to
it
be
does.
able to
It does
predict.
not provide
So
you with
that's all it does. It does
it
not
won't
provide you
give
with
you
a
an equation or anything like that. I
won't
mean,
give you an
for
equation or
some
anything like
models,
that. I
you can
mean,
actually derive.
for
If you use
some
just a simple
models, you can
multivariate
actually
regression,
derive. If you
you
use
will
a
have an
simple
equation.
multivariate
But
regression,
for deep
you
learning
will have an
models,
equation.
the equation is
But for deep
implicit.
learning
Right? It is
models,
all
the equation is
statistical. It is
implicit. Right?
just
It is
the
all
training data set. If you
statistical.
have
It
the
is
training data
just
set, the
the
physics
training
is
data
in
set.
the
If you
training
have
data
the
set.
training data set, the
Actually,
physics
the
is
physics
in
in
the
the
training
training
data
data
set.
set is
Actually, the
more
physics in the
than the
training data
physics
set
that we
is
might have,
more
because our
than
physics
the
models
physics
are
that we might
imperfect,
have
right? We
because
have
our physics
approximations,
models
so
are
forth.
imperfect,
But
right?
the
We have
training data set,
approximations, so forth.
of course,
But the
it
training
captures
data set,
all of the physics. What is
of
physics?
course,
But
it
also
captures all of the physics.
data
What
always
is
has
physics?
some
But
errors,
also
right? It is not
data
perfect
always has
data.
some errors,
So
right?
it
It is
has
not
all the
perfect data.
physics,
But
so
it
it also
has
has
all
some
the
errors,
physics,
and so that
but it
that's
also
also an
has
issue.
some errors, and so that's
yes
also
sir
an issue.
got it yes sir
Sir,
thank you sir thank you sir
uh,
thank you sir
sir, I have one more question, sir.
sir
Could you
I
please?
have one more question
Yes,
sir
sir.
could you please
Yes, sir. You generated you
like
generated
a
a prior model of feces like
a prior
let's
model
say
of
like
feces like
5,000 model,
let's say like
right? And then you
five
use
thousand model
data
right and
and
then you use
calculated the
data
likelihood
and
of
calculated the
Well, so
likelihood
so far there is no
of
data. There's no
Well,
so far
observed
there is
data,
no
right?
data. There's
There
no
is
modeled
observed
data, right?
geology,
There
the
is
facies,
modeled
and there is modeled
geology,
data,
the facies,
right? So
and there
from
is
that facies
modeled
model,
data.
we populate
Right? So
that with
from that facies model,
VPBS
we
density,
populate
and
that
then
with
we forward some of the
VPBS
sizing. So
density, and
now
then we
we
forward
have
some of the
the
sizing. So
facies
now
models and the
we have
corresponding
the
seismic data.
facies
So this
models
is
and the
model.
corresponding
Facies
seismic
model,
data. So this is
that is
model.
geology, and we
Facies
have the
model.
seismic data. So now
That
we
is
have a
geology,
collection
and we have the
5,000
seismic
data.
data. So now we
Facies
have a
models and
collection
5,000
5,000
seismic data.
facies
None
models
of
and
this is
5,000
actual
seismic
observed
data.
data, right? So
None
this
of
we
this is
use just
actual
to
observed data, right?
train
So
the
this
machine
we
learner
use to
just to
train the
the
machine
relation,
learner
the
to
nonlinear
learn
relation between
the
the
relation,
facies
the
and the seismic
nonlinear
data.
relation between the facies
Once
and
it
the
has
seismic
learned
data.
it, now we give
Once
it
it
a
has
new
learned it,
seismic
now
data, the
we
actual
give it a
observed seismic
new
data.
seismic data, the actual
And with this
observed seismic
observed
data.
seismic data now,
And with
it
this
can then
observed
predict
seismic
the
data
facies.
now, it can then
So, sir,
predict the facies.
there will be like
so sir
if we have
there
like
will be like
5,000 prior,
if we
so
have
we
like
will have like
5,000 prior
5,000
so we will
posteriors,
have like
like in that
5,000
No, 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 no,
posteriors
no.
like in that
You'll have
in,
no.
You'll
You'll
select
you'll
some of
have
them
with the
you'll
which
select
are
some of them
close to
with
what you're getting, right?
which
So
are
the posterior
close
might be
to
just
what you're
30,
getting.
right? So the
You won't
posterior
have
might be just
5,000.
30. You won't have 5,000.
okay, sir. Thank you. I'll
Well,
okay, sir. Thank
let's
you.
see.
I'll
Is there a
Let's
blackboard
see.
here?
Is there a
Do
blackboard
we have
here?
a blackboard?
Do we have a
Or a
blackboard
whiteboard, right? So let's see if I
or a
can write there.
whiteboard, right? So let's see if I
yes,
can
sir.
write there.
Thank you. Yes, sir. Thank you.
Okay, so starting a whiteboard. Okay, so starting a whiteboard. Can you see that? Can you see that? Can you see the whiteboard?
Yes,
Can
sir,
you
sir.
see the
I'm trying
whiteboard?
to. Yes, sir, sir. I'm trying to.
Are you
you able to see the whiteboard or not? Are you able to see the whiteboard? Okay, I have to
No, sir.
share. Okay, I have to present to the meeting. Share. Present to the meeting. right? So you see this. Now you can see the white. So you see this.
Yes, sir.
Now you can see the
Okay,
white.
so
Yes,
so
sir.
let's say this is our prior. So it's
so
of
let's
course
say
in
this
high
is our
dimensional
prior.
space, but
So it's of
conceptually
course in high dimensional
we have the
space,
prior,
but
and now
conceptually
we have the
let's
prior,
say
and
that
now
these
we
are
have
all our models, 5,000
let's say that
models,
these
right?
are
So we
all
have
our models,
a broad
5,000
distribution
models,
of
right?
the
So we
prior.
have a broad distribution of the prior, and so let's say this is our seismic data that we have created, right? So
Seismic
we
data
have
that we have
5,000
created,
geology
right?
models,
So
and then
we have
corresponding that we
5,000
have
geology
5,000
models,
seismic
and then
data,
corresponding that we
and
have
this is a
5,000
projection
seismic
of
data.
that high
And this
dimensional
is a
space in
projection
some
of that
conceptual
high
low dimensional
dimensional
space,
space
let's say,
in some conceptual
in
low
some sort of
dimensional space,
PCS
let's
space
say,
or MDS
in
space. So
some
just
sort of
conceptually,
PCS
we
space
have
or
this
MDS
5,000
space. So
models.
just
And
conceptually,
then
we
what we
have this
have
5,000
is
models.
that,
And then what we have
that's
is
our
that
prior. Now,
but
so
now
that's
let's say
our
that
prior. But
we
now let's
have
say
the
that
Are
we
yes, sir.
have the
Sorry.
data.
Are these like
Yes, sir,
images?
go ahead.
I mean, these like
These are
images?
representation. Yeah, each
I mean,
each dot is the
representation.
full
Yeah,
seismic
each
image,
dot
right?
is the
But
full
I'm representing it
seismic
in
image,
a
right?
low
But I'm
dimensional space. So
representing
each
it in
dot is
low
one
dimensional
full
space. So
representation
each dot
of
is one
geologic
full
model as
representation
well as the
of
corresponding seismic
geologic
data, right?
model as well as the
Each dot
corresponding
represents
seismic
one of
data,
them,
right?
right?
Each
Now we
dot
have the
represents one of them,
observed
right?
seismic data, right?
Now
So
we
these were
have
the
the prior. Now we
observed
have the
seismic data,
observed
right? So
seismic
these were the
data,
prior.
and now we have
We
the
project that
observed
to the
seismic
same
data,
space, and that observed seismic
project
data
that to the
falls
same
over here.
space, and that observed seismic data
Then
falls
what we
over
can say
here.
is, okay, with this
Then what we
observed
can say
seismic
is,
data, we
okay,
can predict
with
this
this
from the
observed seismic
CNN,
data,
and
we
we can
can predict
predict
this
this model
from the
and
CNN,
that
and we
facious
can
model.
predict
Now
this
let's say
model,
that facious
and
model
that
falls
facious
over
model.
here.
Now let's say that
Now the
facious model falls
posteriors
over
will
here.
be
Now
just
the
this set,
posteriors
which are
will
kind
be
of close to those
just this
observations.
set,
So now
which are
these
kind of
the
close to
other
those
models in the
observations. So
priors
now
they will
these
be
the
rejected. Right?
other
So
models in
these
the
models
priors
are
they will be
rejected.
rejected, right? So
So
these
we
models
reject
are
those
rejected.
models
So we
because they
reject
are
those
not close to
models
our observation.
because they are not
So
close to
those
our
are rejected
observation.
from the
So
prior. So
those are
initially we had
rejected
5,000
from the prior.
and
So
now what we
initially
are
we had
left is only
5,000,
these models,
and
which are
now what
maybe
we are left is
50
only
or
these
30 or
models,
whatever.
which are maybe 50 or
So
30 or
sir.
whatever. Yeah.
Yes,
So that's
does that mean that does that mean that we actually found out the uncertainty of our predicted solution, of our
approximately.
predicted
This is called
solution?
approximate Bayesian
Approximately,
computation.
this
So
is called
yeah,
approximate
because
Bayesian
to
computation. So
do
yeah, approximate
rigorous
because to do
uncertainty, you would either have to
rigorous
do Markov-Chain Monte Carlo
uncertainty, you
or
would
just
either have
pure
to do
rejection
Markov-Chain
sampling,
Monte Carlo or
which will
just
be
pure rejection
computationally
sampling,
very
which will
costly.
be
But
computationally
yes, this is an
very costly.
approximate. But yes, this is an
Right.
approximate
Yes, sir. So
uncertainty. Right.
does that mean like we use like Markov chain Monte Carlo instead of using
Adam
instead of using
Forest,
Adam optimization,
Forest,
No, no,
like
no. We
Adam
always use Adam of
optimization?
that's it in the training
We
part, right?
always
That's a
use Adam
training
of
part.
that's it in the
So
training
Markov-Chain
part, right?
Monte
That's a
Carlo, we don't
training
use
part.
Markov-Chain
So
Monte Carlo.
Markov-Chain
Here we
Monte
do
Carlo, we don't
ABC,
use
approximate
Markov-Chain Monte
Bayesian
Carlo. Here we do
computation,
ABC,
which is
approximate
much
Bayesian
more
computation,
numerically
which is
efficient
much more
compared to Markov-Chain Monte Carlo.
numerically
So we don't.
efficient compared to
We could do
Markov-Chain
that,
Monte
of course.
Carlo.
If
So
we
we
did
don't.
Markov-Chain Monte
We
Carlo,
could do
then we
that, of course. If
wouldn't
we did
train a
Markov-Chain Monte
machine
Carlo,
learner
then
at
we
all. Then we
wouldn't
just do
train
Markov-Chain
a
Monte
machine learner
Carlo.
at all.
Of
Then we
course,
just
if
do
we did,
Markov-Chain Monte Carlo.
we would not
Of
be
course,
able
if
to
we
find
did,
the posterior with
we
just
would not be able
5,000
to
samples.
find
It
the
would have to be
posterior with just 500,000
500,000
samples. It would have to be
samples in the Markov chain
500,000
to get to the
samples in the
posterior,
Markov chain
Yes, sir.
to get to the posterior.
Yes, sir. I'll read the paper
yes,
for
sir.
more information.
I'll read the
Thank you.
paper
Thank you
for
for
more
explaining.
information.
Okay.
Thank you for explaining.
Okay.
How to deal with this uncertainty that how to deal with this uncertainty that computations will be more in this case, computations will be more in this case.
What was that? I didn't get the audio. What was that? I didn't get the audio.
Sir, I was asking in this case, sir, I was asking more uncertainty. In this case, sir, you are putting with more uncertainty.
What do you mean
You are
more
taking
uncertainty?
what do you mean
What do you
more
mean more
uncertainty?
uncertainty?
What
What
do you
is
mean
more
more
uncertainty? What is more uncertainty?
I mean, sir, in case, sir, I mean, sir, that they will be giving to some data set, they will be giving to the probability that, for instance,
I can't hear you properly. Maybe you should write in the chat. I cannot hear you properly. Your audio is not coming clearly. Maybe you should write in the chat. Maybe you should write in the chat.
Sir, I have one more question.
Okay.
If you don't mind. Yes, sir. Sir,
Okay.
can we generate it? Can we generate this kind of images instead of from seismic migration or something? Like and using like seismic migration, we generate this kind of image, and then if we have some data, we can apply this kind of technique to find the
find the
models. posterior models.
Yeah, you could, but your question is not clear. So you haven't defined your question. Is not clear. So you haven't defined your question. Your question. You're not clear about what your question is. You're not clear about what your question is. Migration images. What do you want migration images, and then what do you want to predict?
Sir, sir, what I want to do is from the data I should be able to get from the data I should be able to get my data can be from my data can be receiver functions or teleseismic receiver functions or
thing, right? What we are doing here is a very different thing, right? What we are doing here is post-stack sizing data, or partial stack sizing data, or near angle stack, partial stack sizing data, near angle stack, far angle stack, mid angle stack. Okay, so you have telesizing data. Okay, so you have telesizing data. You have seismograms, right? Telesizing, you have seismograms, right?
Yes, sir.
Telesizing, what do you want to predict?
Yes, sir.
And what?
Yes, sir.
What do you want to predict?
Yes, sir. From teleseismic seismograms, we can generate teleseismic seismograms. We can generate of the subsurface reflectivity image, and then of the subsurface. And then if further I have another data set. I have from that I should be able to predict. From that I should be able to predict a reflectivity image of the subsurface, like a reflectivity image of the subsurface, like.
So right now you say you have teleseismic data. So right now you say you have teleseismic data, and you do that. That's an inversion, right? So how do you do that? That's an inversion.
That can be done using by using some tomography technique. By using some tomography technique, we can find
that's a conventional traditional inversion technique. That's a conventional traditional inversion technique, right? So it's framed as an optimization problem. So you framed as an optimization problem. So you optimize a model, and then you optimize that based on some model, and then you optimize that. You do that some gradient. So now if you have another data set, you could apply the same technique and get the. You could apply the same technique and get the other data set reflectivity for that.
Yes, sir. That's what. Yes, sir. Yes, sir. That's
what. So now, if you're just right, so one data, right? You have one telesizing data. One data, right? You have one telesizing inversion and get the reflective image. So that's inversion and get the traditional image. So you have another data set. You can again apply. You have another data set. You can again apply the tomographic inversion and get the all clear image. So what is your question? All clear.
Yes, sir.
So what is your question?
My question is like, my question is like, if I can generate like such kind of images, if I can generate such kind of images, CNN, right, and train on the CNN, and then on those images, if I have like, and then after that, another, if I have like another data set, then
do that. So then make sure. Make sure that your training set that you have, make sure that your training set is broad enough in the CNN to capture all kind of different scenarios. To capture all kind of different scenarios.
Yes, sir.
Right. Let's say that you only have. Right, let's say that you only have. I'm not teleseismic expert, but let's say you have teleseismic expert, but let's say you have earthquakes coming from one particular earthquakes coming from one particular, and then your data set will be biased, right? You only have data for that will be biased, right? You only have data for that data set that covers all different kind of data sets that covers all different kind of earthquakes. It is within that training set. It is within that training set.
Yes, sir. So I will have to like I will have to take care of like I will have to take care of like or the direct epicenter locations or the like directivity of the earthquake.
Probably you have to also take care of what is probably you have to also take care of what is lithology is, where is originated epicenter is, if it is originated types of lithology, if it is originating different types of lithology or different types of tectonic environments,
like the source location and source parameters, like the source location and source parameters,
directivity, like I said, all of those you have to have broad coverage. Like I said, all of those. Otherwise, you have broad coverage. Let's say only have telesizing. Otherwise, they're coming from the east. Let's say only have telesizing data coming from the new one that is, and then you try to predict a new one that is maybe that coming from the west or north or south. Maybe that will not work.
Thank you, sir. Thank you, sir. Sir, by the way, I'm pursuing PhD. By the way, I'm pursuing PhD at Baylor University in PhD in seismology. So I'm PhD kind of like I'm looking into kind of like looking into methods, and I'm planning methods, and I'm planning to implement like this kind of methods in my PhD. This kind of methods in my PhD.
Good.
Thank you.
How to deal with uncertainty? So the question: how to deal with uncertainty? So the question from well, you have to define what are your uncertainties, and then what are your tries them mathematically, and then you want to parameterize them mathematically. Quantify that. So first you define what are the uncertainties, then you parameterize what are the uncertainties, and then you create distributions for those parameters, and then you create distributions for those parameters. It's not easy, but there are some systematic ways of doing there are some systematic doesn't mean that you'll always be able to, but that doesn't mean that you'll always be able to, right? There's nobody could have predicted the pandemic, for example. Nobody could have predicted the pandemic, for example, right? There's always the black swan events. So how to deal with uncertainties is a big question. So how to deal with uncertainties is a big question. It's almost more philosophical than geoscience. Almost more philosophical than geoscience. What do you believe was a revolutionary achievement of AI? What do you believe was a revolutionary achievement of AI in geoscience? I don't know. Maybe it is. Who knows? Something in the future. Lots of different achievements, but lots of different achievements. Right? How do you define revolutionary achievement? What do you mean by revolutionary achievement? Okay. Any other questions? Okay. Any other questions?
So I think there is no other question. So I think there is no other question. It was our pleasure to have you, sir. It was our pleasure to have you, sir, and the level definitely serves us and will definitely working as a professor in the Department of Energy Resources Engineering by courtesy of Geophysics and Geological Sciences at Stanford University. He has received his bachelor's and master's degree in geophysics from Banaras University, India, and his doctorate of philosophy in geophysics from Stanford University. Sir has also co-authored the Rock Physics Handbook, Quantitative Seismic Interpretation and Value of Information in the Earth Sciences, which received the Publication Competition Finalist Award from Decision Analysis Society. Sir has received Best Paper Award from the Society of Exploration Geophysicists and the International Association of Mathematical Geosciences. In today's world, machine learning has proven useful for a very large number of applications in many parts of Earth science system. And today, sir is here to tell us about the recent advances in geosciences and machine learning, pitfalls and opportunities. I would like to inform all the participants there will also be a brief question and answer session after the talk, for which you have to type your question into the chat box. We will also provide you a feedback form that we can improve our upcoming lectures. So please note that the form will contain two questions related to talk. Participants who fill the form, only those will get the certificate. So do fill it. Also, for your prior information, the whole session is being recorded so that we can upload it to our YouTube channel. So now I think we are good to proceed. I would like to call sir to take over. Sir, please.
Thank you. Thank you for your introduction. Let me share my screen and we'll get started. Okay, I hope you can see the screen.
Yes.
Are you able to? Yes, okay, all right. So let's talk about machine learning in geosciences. Machine learning has been around for quite a while in the geosciences, but let's see what is new. So as you mentioned, and we have seen, machine learning has experienced rapid growth. And when you talk about machine learning, of course, there's artificial intelligence, then a subset of that is machine learning, and a subset of machine learning is deep learning. Deep learning particularly has grown very rapidly. So what are some of the challenges and opportunities for adopting these kind of modern machine learning techniques for geoscience research? So what are some of the applications of traditional machine learning? Classification, or supervised learning. Then we have clustering, unsupervised learning, nonlinear regressions. Those are all various applications of machine learning that have been around in the geosciences for many decades. Right, so here's a little bit of history: seismic reservoir characterization, rock physics, and machine learning. In the 1980s, that's more than 40 years ago, there were empirical regression models based on data. Then later on, there were applications of ANN, artificial neural network, for Bayesian classification of lithologies and fluids, Bayesian machine learning for shelly sands, sub-resolution shelly sands. These have been around for 20 years or so. And also before deep learning, there were kernel methods, kernel-based methods that was quite popular at that time. And these have also been applied in the geosciences. So what are some of the algorithms of traditional machine learning? There's, of course, very classical discriminant analysis that has been around for almost 100 years now. Bayesian classification, of course, kernel methods I mentioned. Artificial neural networks have been around, and then trees and random forests. Those are also very useful for classification and regression tasks. And now more currently deep convolutional neural networks. But even these deep convolutional neural networks, they actually have been around for some time. So if you look at when neural networks started, it started first with Pitts and McCullough in 1943. Then there was the Perceptron, 57, Neocognitron, and CNN, which is the convolutional neural network, was there since the mid-1980s. So they have been around for a while. Let's see what is a neural network and what is a CNN, very simply. Many of you probably already know this, but let's see what this is. So first we'll start with a single neuron, or what is called a perceptron, which is the basic building block. So what this does is, let's say we have some inputs, x1 to xd inputs. And so the neuron, it multiplies those inputs by some weights, wi. So this is just a linear combination of the inputs plus what is called a bias, or just a constant, right? So this is a linear plus a constant. So that's an affine function. So it takes an affine function of the inputs. Very simple, right? So z equals w dot x plus b. Then it passes this through some nonlinear function, right? So this nonlinear function in neural networks, that's called an activation function. And so now this could be there are various types of nonlinear function. You can see that. And so this is just a way of creating a nonlinear output y, which is a function of the input x. Right? So wx plus b, that's the linear plus a constant. And we propagate that through some nonlinear function. These days, this nonlinear function called the ReLU is very popular, but the others are also quite useful. The sigmoid function, the hyperbolic tangent function, those are also useful nonlinear functions. So this is just a way to systematically build a nonlinear function of multiple inputs. Okay, so that's a rectified linear unit. Now, instead of having a single neuron, we can have multiple neurons, right? So we have X coming in, and now we have Xi. This is a layer of multiple neurons. All of those, we multiply the weights with the inputs and pass it to all of the neurons. Plus, of course, we add a constant term. And we can have, instead of just a single layer of multiple neurons, we can have multiple layers. Right? So that's multiple layers of neurons. And what this is it creates a nonlinear function of the input, which is parameterized by these weights. And we can find the weights by doing the optimization problem by minimizing of the neural network is close to the y that we have in a training data. So that's all it is. It's just a way of fitting a nonlinear function to some data. It's a systematic way of fitting a nonlinear function. So if that output y is a continuous variable, then it's a nonlinear regression, and we minimize the least square error. On the other hand, if y is categorical, let's say we want to predict different facies, brine sands, oil sands, gas sands, shales, and it's a categorical, so then it's a nonlinear classification problem. And what we want to minimize is the misclassification error. So that's multiple layers of neurons. It's just a way of building nonlinear functions. Now, what if this x is not just a single scalar input or 4 inputs like a vector like that, but what if it becomes an image? So now if the x itself is an image, and each neuron now it is a convolution filter. It could be a 7x7 or 21x21 convolution filter that we apply on this image. And of course, this image can be 2D, or also it can be an array, a 3D or even higher dimensional arrays of numbers. And we have this filters. It's just a usual convolution filter that we learn about in geophysics, signal processing, same convolution. Of course, we still have our nonlinear activation function. And then there are some additional tasks that is also there, some additional functions that take place. For example, we can pool the inputs together. It's called max pooling, or we can average them together, and so on. So that's essentially a convolutional neural network. So like I said, these have been around. Even this convolutional neural network is nothing very new. It has been around in the literature and with researchers since the mid 1980s. So what has changed now? Why such a big hype about convolutional networks and deep learning? So what has happened is that there's a phase transition in the way we do computing, and this is as a result of multiple things coming together. So what are some of those things? So one is, of course, the mobile revolution, right? We have smartphones that are growing faster than the population itself. Right? So lots of smartphone users. This data is already old, probably now there are many more. So that's a big revolution. And so smartphones, they are creating, you can find smartphones even in the remotest places, right? Remote villages, even in monasteries, they have smartphones now. So this is creating a lot of data. This mobile revolution is creating a lot of data. And for example, every 60 seconds, about 2 terabytes of data is created, and it is uploaded to the clouds, right? Pictures, songs, messages, everything. So this huge data that has come about as a result of the mobile revolution, it has also given rise to global database services and an explosion of computational resources, because that data is being uploaded to the cloud and it's being transferred from one place to the other. You're sending pictures, you're sending images, sound files, and so on. So there's the cloud paradigm, and millions of businesses now rely on cloud computing. And so now we can get thousands of hours of CPU at a fairly cheap cost. So that's another big transition, big change that has happened since the 1980s. Right? In the 1980s, we had CNNs, but we didn't have this mobile revolution. We didn't have this cloud computing. Right? So every 60 seconds, 2 terabytes of data is created. And now businesses, they want to make money from the data. They want to advertise and use the data in a way to make more money, make profit. So that's one part of it. Then the other part is the rise of GPU chips, right? And partly driven by the global games market. It's a $100 billion industry. And so that has driven the development of very fast, very efficient, good GPUs. And as a result of that, now we can do lots of computing much better than what we could do with CPUs. And you can see here, we have a 50x boost in deep learning because of the advent of GPUs. You can see that in the graph there on the left, GPU versus CPU. Gaming industry has given rise to development of good GPUs, and that has helped machine learning speed. And then there has been development of frameworks for deep learning, frameworks such as TensorFlow, PyTorch, Keras, and so forth. And this allows scientists, not computer scientists, but other scientists like geoscientists, this allows us to use deep learning without having to develop everything from scratch. If you were a geoscientist in the 1980s and if you wanted to use CNN, we didn't have TensorFlow or Keras there. You would have to write your own code from scratch, and that would be a big challenge. But now, because we have these frameworks readily available, geoscientists, we don't have to be computer scientists. We can take those frameworks and start developing our own deep learning models. And these deep learning models have now begun to beat human performance in many computer graphics applications, such as here, where we see that human performance in classifying images, that's around 5 to 10% error. But in 2015, deep learning networks like the RECENY, that outperformed human performance. Also, we see other kind of machine learning, deep networks, plus other advanced research methods that has helped machines to beat humans in games like Go, AlphaGo, and chess, and so forth. Go is supposed to be a game that is many more times complex than chess. I don't know the game itself, but you must have heard of AlphaGo, how that they defeated the world human champion. So now artificial intelligence, machine learning, deep learning has become a big business. Right? So McKinsey reports that there's a huge value of deep learning. All that is good. So what does this mean for geoscience research? So now, because of all of these things coming together, because of phase transition in computations, science, the way we do scientific research, computational research is changing. Right? It has changed. There has been a phase transition. So the conventional approach would be to invert a model. We have some data, we invert that data using some physics, we create an Earth model, and then based on that Earth model, we make some predictions. That's a conventional approach. And it's challenging because inversion is non-unique and there are problems with that. And then from the model, we have to make predictions. So for example, we might have seismic data. We invert that seismic data to create a model of not only the impedance, but from that impedance, we have to go to facies, porosity, and so on. And then once we have that Earth model, then we forward simulate the flow in that Earth model, and we want to make some predictions about the flow behavior in the future. So we have data, we have model M, and we have something that we want to predict, which is H. For example, might be the flow behavior of a oil and gas reservoir, or you might be interested in flow of contaminants in a groundwater reservoir, or containment of CO2 in the subsurface. So that's a prediction. So that's a conventional approach. You go from data, we do an inversion, very challenging problem, we go to the model, and from the model, we go to predictions. But now with the machine learning approach, what we can do is we can flip the arrows around, and we can start from the model, and we can create a Monte Carlo simulate. We can create a large number of data D and a large number of predictions from that model. We can forward compute it. So this is much easier. There's no non-uniqueness there, no ambiguity. It's just a forward physics. And once we have a training data set of D and H, then we can use a machine learning model to learn the relation between D and H. So there's no explicit inversion. We directly infer the relation between H and D. And then, of course, when we have a particular D observed, then we can use that machine learning model to predict H for that particular D observed. So that's a different way of doing modeling these days, doing prediction without having to do explicit inversion. So, but of course, there's a greater emphasis on the prior model, the geologic model. So what are some of the opportunities and challenge? So machine learning requires training data, label data, and in particular, deep learning requires a lot of training data. So we of course have a lot of data in geophysics, but we do not have a lot of labeled data. So that's one of the challenges. Unlike computer graphics, in computer graphics, you have many images that people have collected, and you know the labels, right? So you have cats and dogs, for example, and then you can train the network with this labeled set, and then the network after training will be able to predict for new images. So for example, in computer graphics and business applications, ImageNet, that's a labeled data set. It has 14 million labeled images, right? Each image has a label. And so that's nice. You can use that to train your network. But we don't have those kind of labeled data sets in geoscience. We don't have well logs at every seismic trace. Of course, if we had well logs at every seismic trace, we would not need to do any machine learning. So what we need is domain knowledge to augment the machine learning. We have some training data, but we need to augment that training data by using domain knowledge, by using physics, combined with statistics. So pure machine learning is purely statistics, data-driven, but we combine that with a domain knowledge, which is physics and geology. So when we take advantage of both of them together, then we can have better predictions, and with better predictions, we can make better decisions. All right, so now let's look at some examples. Rock physics guided deep convolution networks for seismic impedance inversion, reservoir facies estimation from seismic data by semantic segmentation, and then geobody interpretation using UNet, which is another kind of deep network. So we have seismic impedance. What we want to know, we have a seismic trace, and we want to use a CNN, a deep network, to predict the P impedance. So that's impedance inversion, but not in the usual traditional sense of impedance inversion. That was the usual way of doing it, but using machine learning. Right? So we're going to open up this box. It's no longer a black box. So it's like I said, it is relatively easy to build a neural network and predict on the data set. But what are some of the questions? How good is a network's generalization power? Can it generalize to types of data that it has not seen? So can it extrapolate for unseen scenarios and uncertainty quantification? So of course, again, like I said, there have been many applications of neural networks, artificial neural networks, ANNs, in geophysics. And some examples are given here, non-exhaustive, of course, there are many more. And those have been around, like I said, from the 1980s, 90s. They have been used for inversion of seismic data for elastic attributes. Tarantola used that. Lithology and permeability prediction from well logs, and also for full waveform inversion. That's more recent. So let's see how we do it. So we have to use synthetic modeling using rock physics and wave propagation to generate the labeled training data set, because we don't have that fully labeled training data set. Then, of course, there's building the neural network architecture, hyperparameter tuning, and then systematically testing the performance of the network and the generalization capability of the network. So let's go through the workflow one at a time. So how do we generate the labeled data set? So that means we need to have pairs, many pairs of these impedance and the seismic trace, corresponding seismic trace. And that's a labeled data set. So to generate the labeled data set, we have to start with the geology first. So we have to have some idea of the geology, the facies, in this case sand and shale, how they're distributed vertically, what is the spatial correlation. So we have to have a model for that spatial correlation. Then for those different facies, we have to assign their porosity. The different facies have different distributions of porosity, clay content. From that, we put those into a rock physics model, which will give us the elastic parameters, VP, VS, and density. From VP and density, we can get the impedance. And once we have the impedance, we can do wave propagation to compute the seismogram. So here, for the geological part, we use what is called sequential indicator simulation. We could also use other kind of Markov models to create that geology that accounts for the spatial correlation between the facies. Then we have to populate that with porosity and clay content. So there again, we use a method called sequential Gaussian simulation. It is a spatial simulation method. Then those things are used as input into a rock physics model. And then rock physics model gives us the impedance. And then we have full waveform seismogram modeling that gives the seismic trace. So now we have this pairs of impedance and seismic trace, which is our labeled data set. Of course, we do this for many thousands of realizations. So we have 2,000 traces, and this is divided into a training set, a validation set, and a test set, about 70, 15, 15. Nothing hard and fast about that, but those are typical divisions. And then there is the training, right? So there will be the input architecture, the seismogram will be the input, the output is the known impedance, and then with those two input and output, the weights will be optimized such that the neural network gives the right output. Right, so that's the training phase. And then once it is trained, then in the prediction phase, it will have a new seismogram, a new input seismogram, and the output will be a predicted impedance trace. So then we train them on different examples, and then after training, here are some tests. We see how it performs. So here we have the test set, which the neural network has not seen before. And you can see the red is the true impedance, and we can see the CNN predictions in black dotted line. And it does a pretty good job of capturing the distribution of the impedance. We can also get the posterior distribution, the uncertainty around that. That's using approximate Bayesian computation. And so there we have the blue band. So that gives us some estimate of perform when we have a challenge data set. In other words, some a data set where it has not seen that kind of data before. So for example, let's say that we have a rock physics model, and we used, in the training case, regular testing and training, we use some rock physics model parameters, which are given as you see there, 10, 11, 12, 13, 14, and so forth. Some parameters, not we don't have to go into what those parameters are. But now in the challenge test, so CT is a challenge test, RT is regular test. Now we're using some rock physics parameters that it has not seen before, right? 6, 7, 8, 9. And similarly, maybe during the training and regular testing, we have a wavelet, the seismic wavelet, which has a certain range of frequency that you see there, 30 to 50 hertz. While for the challenge testing, we try to see how it performs when it has a frequency that it has not seen before, outside that training range. Right? So rock physics models, wavelet phase, wavelet frequency, and so forth. So let's see how it performs. Now, of course, it doesn't perform as well as the regular testing. You can see now it starts to deviate a little bit. The true is again in red, the prediction is in blue. And so there are some more mismatch than in the regular testing, which is to be expected because it has not seen those before. And so then we can see what is the error for the different scenarios, which ones are the most sensitive parameters. So here we are plotting error on the y-axis. It is just L1, so absolute error. And here we are plotting the different scenarios. So let's say what happens when we change the rock physics parameters. So CT is a challenge testing and RT is a regular testing where it has seen those before. So with regular testing, we have some errors here, of course, around 10%. But you can see now, if the rock physics model is not correct, if it is not seen, then the error increases. Similarly, the wavelet, we have to have a good constraint on the wavelet. You can see the frequency of the wavelet. In the regular testing, if we have the wavelet that is already seen in the training set, again, we have errors around 10, 12% or so. But if you have a wavelet that is quite different, then the error goes up a lot. So that means the rock physics model parameters and the wavelet that goes into the physics modeling, those are important. The source wavelet, the rock physics, and so forth. And of course, there's application to field data. So this was applied to the Volvo field data that was made available by Equinor, the Norwegian company. And so these are some applications of the CNN-based seismic impedance inversion. Okay. All right, so that's how we test the generalization and see where the network will fail and how it will extrapolate for unseen scenarios and so on. Now, that was an example of a supervised learning, but we can also do this in an unsupervised sense. And what we do here is that we have the input seismic trace, we have our CNNs, right? So here we have the CNNs, and then at the end out comes an impedance or VPVS density. But now we don't have any labeled pairs of data, but what we do is we want to, during training, we take this output, so this is now called a latent space, the latent space of the network, and we take that output, we convolve it with a wavelet, right? We compute the reflection coefficients, convolve it with the wavelet, and now we have an output seismic gather. Then we compare that with the input seismic gather, and the loss function now is the difference between the computed seismic gather and the input seismic gather. So once this is minimized, then that's during the training. Then during the prediction phase, we take away the convolution, and this output, the latent space itself, is the output then. So this is nice because now we do not need to have labeled data set. We can just work with a seismic gather directly without having to have a labeled data set. So we can do the supervised, we can do unsupervised, and the predictions are comparable. Both of them are able to predict quite nicely for the VP. Here are some comparisons. So for the supervised case, we require a labeled data set. Unsupervised, we do not require a labeled data set, but we do require the wavelet, and more importantly, we require a low frequency background model, which we do not need for the supervised case because we already have the training set. The supervised learning is faster convergence, at least in our example. The unsupervised was a little bit slower. All right, so that's an example of impedance inversion using convolutional networks. But of course, impedance by itself is not what we're interested in predicting. You cannot just take high impedance and then go to the market and sell impedance. What we really need to know is how the reservoir will flow, what will come out of it if you produce it. So that means we have to go to the facies, reservoir facies. Where are the sands? Where are the shales? So this next study is about reservoir facies estimation by semantic segmentation using, again, deep networks, deep convolutional networks. So here's our workflow, right? So we have to have some prior information about the geology. We have some uncertain quantification, and we want samples from the posterior. We want to sample from the posterior distribution of reservoir facies given the observed seismic data. and we have to do it in an efficient manner. Of course, these distributions are high dimension, very high dimension. And so here we have the Bayesian approach. We have a prior. This is the prior of distribution of all facies models for that geology, of course. And it is, of course, high dimension, not just a univariate distribution. Then we have the likelihood of the data given that facies model. And then we have the posterior, and we want samples from the posterior. Of course, since these distributions are so high dimensional, we cannot even explicitly write down those distributions. And what we can do only is to sample, get realizations from the prior, weighted by the likelihood, and then realizations from the posterior. So how do we do that? Again, now we are going to do it using machine learning. So instead of doing this inversion, we'll not do the inversion from seismic data to elastic properties and elastic properties to the facies, but we'll do just Monte Carlo simulation from the geology to seismic data and facies, and then create a training data set, which will then be used to train the network, deep network. So we'll define the prior on the target, which is the facies. We'll sample from the prior to generate multiple facies models. From that facies models, we have to go to rock physics and wave propagation to simulate the seismic data. Then we will learn the relation between the H and D, and from that relation, we can then predict directly the facies for a given D observed. Right? So that's our workflow. So here in this case, we use a different geostatistical method called multiple point geostatistics to create the realizations from the prior. So this is a channelized environment. So we have some background shales, and we have some channels of different thicknesses and widths and so forth. And the channels have different fluids. Some of them are oil saturated, some of them are brine saturated. So we create multiple realizations using multiple point geostatistics. So that's a geology. Then we have rock physics models that use the VPN density, so geology plus rock physics. And then we have the forward seismic modeling, which is full waveform normal incidence seismogram with a 35 Hertz wavelet. And so that gives us a seismic data. And so now we will train the deep convolutional neural network to learn the relation between the seismic data and the corresponding reservoir facies model. And so this will be our deep convolutional neural network, a semantic segmentation. And so here, other details, we use what is called dilational convolution filters, such that it exponentially increases the field of view. So in that way, we can have a larger field of view without increasing the number of filter coefficients. And so here we have the original filter, then we step it out by steps of 1, then steps of 2, and so forth. So we still have 9 filter coefficients, but with a larger field of view. So that is quite useful. Then, of course, there is a training. We train that, we optimize the parameters. So it is trained on 1 GPU, and it takes about 5 hours. And so we have the training set error, 94% performance. That's pretty good. Validation is 92. On the test set, that's 92. So that's pretty good there. We can also see what it has learned. We can actually go into the layers, and we can look at the different slices in the layers, and we can see where it is activated. And so we can see, for example, in a particular layer, layer number 7, the third slice, it is activated actually by the oil sands, the red facies here, the oil sands. That's what is activating this layer over here. So we have to, of course, evaluate if the model is overfitting. So we should not have very high accuracy in training set, but then if it is poor on the test set, that means it is overfitting on the training set. We can also see what is the upper bound on the accuracy with the Bayesian classification with true impedance, with the perfect impedance. So what is the optimal Bayes error, the best that anybody could perform, any algorithm could perform, right? In this case, we have a synthetic data set, so we can test that. So the upper bound, right, this is the Bayes error with the true impedance, the perfect impedance. If we knew the impedance exactly, we could classify the shales. So here we have higher impedance shale, then we have the brine sand, middle impedance, and then we have the oil sands, which are lower impedance. So if we knew the true impedances, the upper limit would be 97.1, right? That's the best any method could be able to do for this case. How does the CNN compare to that? And how does the traditional machine learning algorithm compare to that? So if we can just, if you do classification, standard classification with seismic impedance, with a low resolution seismic impedance, how does that perform? So this is, we can call this traditional machine learning, Bayesian classification. Right? So now we see that the classification accuracy is 82%. Compare that to 97%. Right? So traditional machine learning or traditional Bayesian classification works well, but it gives a lower accuracy of 82%. How does the CNN do? Well, if you look at the CNN, you see that there's a big gain in accuracy, 92%, right? So compared with traditional machine learning, 82% alone, and the upper bound is 97%. Of course, if you look at the computation time, Bayesian classification is very simple. Training and prediction, everything takes barely 2 minutes, so it's very easy. Compared to that, the convolutional network, you have to set up the network. There's a training time, hyperparameter tuning, so that will take hours. Creating the data set itself will take some time. But once it is trained, again, the prediction time is quite fast. And after the training, you get a big jump in the accuracy. You get a 10% improvement in accuracy. And of course, that will go on to an improvement in your predictions and decisions. And then, of course, that can be applied to the field application. So this is an offshore Pleistocene slope channel system. So it's a turbidite system. And then you can see how the convolutional network is predicting the different channel phases. So we have the sand channels, and we have below this is the water table contact, oil water contact. So below that, we have the brine sands. Above that in red, you have the oil sands and so on. We can also use machine learning for geobody interpretation. And here's an example. This is a nice example of interpreting the channels and so forth. This is using a different kind of network. This is using a UNet. And so we have the input image, and that is then collapsed. It is encoded down into a 1024 sort of latent vector. Then it is decoded back into an output segmentation map. And of course, there are these links, cross links across the two encoding and decoding parts. That's a UNet. That also performs very well, and that's an example of that. And of course, then you can see that, of course, again, training takes time. So, but what about human experts? What about training a human expert to do this interpretation? Well, that also takes time. So human being, they have to go through at least a master's level course in petroleum geoscience, geophysics, or geology. So that's 2 years of master's work. And then they have to go into the industry and learn how to interpret data until they become an expert. So that also itself is a few years of training. So human expert also require training. What about performance? Now, it might be true that a very highly skilled human interpreter might be able to perform better than the CNNs. That's true. But remember that the human interpreter would take much longer to interpret this whole cube of geobodies, while the machine learning, the network, once it is trained, it predicts the whole cube. It does the interpretation in a fraction of a second, or less than a second. So that's another thing. It's much, much faster, thousands of times faster than the human after it is trained. And then the other thing is error consistency. So let's say that a human expert performs at 95% level, and the deep learning network performs at maybe 92% level, maybe a little bit less than the human. But what happens is when the human interpreter is working on this seismic cube, in the morning when they're fresh, they might be more accurate. But towards afternoon, after seeing many, many inlines and cross lines, they become tired, and their error rate changes. So the error rate doesn't stay consistent. Sometimes it's more, sometimes it's less. They become tired. While the network, it is consistent error. It's the same overall. You can keep on running for hours. You can go through the whole cube. The error is consistent. So there are both pros and cons, and understanding that. So that can be very useful. We can use the machine to do the tedious work with a consistent error rate, and the human experts can really focus on the challenges where it really requires human expertise, and let the machine do the tedious work. So phase transition in the computation machine learning, this is an opportunity. It was not there 20, 30 years ago. We could not do this, but because of all of this, many things coming together, the mobile revolution, cloud computing, GPUs, and the frameworks, now we have different ways of doing things, and so that's an opportunity. Machine learning is not a black box. We can learn the machine. It is nothing mysterious. And we should be able to take advantage of this transition in our research and also for the industry in their business. Of course, there are pitfalls. There are challenges as well as pitfalls. Our training set is important. If it is biased in some ways, that can be a problem. You might have heard of the Google flu, where Google machine learner scientists, they try to predict the flu. This was before the pandemic. It was not the COVID flu. It was a couple of years or more, just the usual flu that comes in the winter season. But because the training set was not correct, it was biased. They were just looking at clicks on Google search, which was not really related to the people who actually had the flu. So they completely mispredicted the progress of the flu. And these are all highly expert machine learning people. So you have to be aware of what kind of training data you have, what is it sensitive to. Like we saw, if your training data does not have the right rock physics model, or if it does not have the right wavelet, then that might be a challenge, right? The prediction will not be so good. So you have to make sure your training set captures all of the different scenarios that you might expect to see when you go to start doing the prediction. So if you can meet those challenges and avoid those pitfalls, then we can definitely benefit from the opportunity this provides us for doing geoscientific research in a new way, in a different way. Of course, we need domain knowledge to augment machine learning. We are not in the field of computer graphics where we can actually get lots of data, label data. For example, when people want to train machines to drive a car in the autonomous vehicles, they can actually put a camera on a car driven by a human person, and they can go on the roads and capture thousands of kilometers of driving with capture the camera and so forth. So they have lots of data. They can just go and collect that. And they have the labels, but we do not have that. We have a lot of data, but not always labeled. So we need to understand our geology and the physics together with the machine learning statistics to get better predictions, and better predictions will ultimately lead to better decisions. All right, so I will stop there, and I'll see if I can answer any questions.
Thank you very much, sir. Sir, we are very grateful to you for delivering such an informative lecture. Now we take our participants' question, if there is.
So where's my meeting? Okay, yeah. All right, so where's the chat box? Okay, I think somebody, all right, let's see. Yeah, for machine learning, is a strong grasp of programming compulsory? Well, some grasp, because you have to use something, right? Like I said, there are all these frameworks that are already out there, so you do not have to go to the basic C++ level of programming everything, but you have to have something at the level of, say, MATLAB and Python at those levels. So you have to have programming. The machine learning, it does require a lot of programming. So you need to have reasonably good grasp of programming if you want to do machine learning.
Sir, good morning, sir. Sir, my name is Banaras. Sir, I wanted to ask a question, sir.
Go ahead.
When we have, yes, sir. I have a question, sir. Sir, when we have more models that will be predicted with the help of machine learning, sir. So how to confirm that, okay, this is what we want? Because if we have more data sets, so there is a possibility always that machine will be giving me more results like models. So we can
no, machine will not be giving you more results. What do you mean by machine will be giving you more results, right? You have to define what's the input and what's the output, right? And so of course you have more data, but then you have to do the training, validation, and testing, right? So that's how you see whether the machine is being trained correctly, not overfitting, and is performing well on the test set. So when you have your, the whole process is very well defined, right? So you have to divide your overall data set into a training set, a validation set, and a test set. Typically 70, 15, 15, but it could be, some other proportions.
And sir, when we have such kind of data sets, I mean, when we are deficient of the data set, sir, so can we correlate with the codes that we are obtaining? I mean, the code analysis.
Well, so then you have to create a data set, right? So then you have to create the data set, right? If you do not have enough data, then you have to augment it using the physics, like we said, right? You have to augment your data set. So first you have to define what is the problem, what is the input, what is the output, right? What are you trying to predict, and from what you're trying to predict, right? So what will be your input and what is your output? You have to define that. Then you have to make sure that you have a good training set. If your original data is not enough, then you have to augment it using geology and rock physics or other domain knowledge. And then you have to, once you have a good training, your data set, then you have to divide it into training, validation, and test, and go through and look at the metrics, the performance metrics, and see whether it is performing okay or not.
Sir, one more question, sir. How do you all deal with when you encounter something which is not actually correct? I mean, different kind of channels or different settings that you get. That may be your own kind of.
Yeah.
And
So that's
right.
Yeah. So you first have to define your prior. So you have to do what is called prior falsification. So let's say that you build a model that is only for say fluvial environments, but your seismic data that you have actually comes from a turbidite environment. Then first, right before you do that, before you start training your machine learning model, you should first do what's called prior falsification. You have to see whether the fluvial environment models you're building, can it even predict statistically? Is it even consistent, statistically consistent with your seismic data? So you'll see that if your seismic data is coming from a turbidite environment and you build all your models based on a fluvial environment, you'll see that that is not statistically consistent with the seismic data that you have. So then you have to throw away that prior model and you have to start fresh with a new prior model. There's a question there from Vishal Pandey for training. I have to look at the other chat questions, right? So we'll look at other people. So for training the machine, we generally use synthetic data. How would it also? No, you don't. You only use synthetic data if you do not have real data. If you have real data, you always use real data for training. You don't use it is not correct to say that we generally use synthetic data. That's not correct. We generally use real data, but our problem is that in geosciences, we do not have labeled real data, right? So we don't have enough. We do not have enough labeled real data. So we have a seismic trace, and wherever we have a well, we have the impedance at the well. So that's one. But how many wells do you have? Maybe you have 10 wells, maybe 20, even 100 wells. That's only 100 pairs of seismic trace and impedance, right? So that's not enough for deep learning. So you always use real data, but then when that real data is not enough, then you augment the real data by using synthetic data.
Sir.
Go ahead.
Yes, sir. Good morning. Sir, actually, my question is like you mentioned that like in the research with Dr. Anshuman Pradhan, you mentioned that you generated the model space of Bayesian posterior using deep learning.
Mm-hmm.
Did I understand that like correctly? I mean, for doing some research into that particular direction.
You understood correctly. The models that are selected afterwards from the network are realizations, at least approximately, from the Bayesian posterior, correct?
Yes, sir. Like to understand the process in that particular direction, like what should I look into? I mean,
you should read the current papers, right? You should read the journals like Geophysics, Mathematical Geosciences, Computational Geosciences. Read those journal papers coming out, and then also read the fundamental basic books in machine learning if you don't have that background, or you can take courses on Coursera, for example. Andrew Ng has a course, right? I hope all of you have taken that course, right?
Sir, sorry for interpreting. Sir, actually, I wanted to like ask is like how did we generated the posterior of so it is a multi-dimensional. It is not just a single parameter like the.
That's correct. It's high dimensional, right? So yes. You sample from the posterior. So you because you have the prior realizations, right? You have those, and then the machine learning, the network learns the relation between all of the prior realizations and the prior generated data, right? So now when you have an observed data, you can see it'll predict which ones are the prior realizations, right? It'll see which are the prior realizations, and so then you get the posterior from that, right? So you get a posterior by selecting what is called approximate Bayesian computation, ABC, right? So you have approximate Bayesian computation where you look at the errors, right? Which ones are the samples which are closer to the observation, right? So you have an observation. So first, before you have an observation, you create the priors, right? You have the model and you have the data, and from the model you create the predictions, which is the H. So H and D, you have a set. You have 2,000, 3,000, 5,000, whatever. So you have created the prior, and then you have the machine learning, which understands, which captures the statistical relation between the D, the prior generated D, and the prior H. Once you have trained that, now you have an observed D, an actual D observed. So now you can say, okay, now you put that into the machine learning, and you can see which ones are close to it, right? So you do what is called approximate Bayesian computation. And so those will then give you the posterior realizations.
Sir, like from what I understand, you generated a list of like prior samples, and from those prior samples, using the convolutional neural networks, you generated the posterior distributions.
No, the posterior distribution is for a given observed data, right? So the prior samples, we have the facies models, and we have the prior data. We also have the prior data, right? So we have 1,000 sets of data D, which is high dimensional, right? It's a seismic section, and we have 1,000 facies models. That's also a seismic section, right? It's a section. It's an Earth model, right? So we have the pairs, and then the machine learning, the CNN, learns the relation between those, the high dimensional relation. And now, when we have an observed seismic data, then it can predict what the corresponding facies is.
Yes, sir. And sir, one more question, sir, please. What kind of full waveform technique did you implement? Like, did you use for?
So in that case, I used Kennett's method. So it's also called reflectivity method, or Kennett's invariant embedding method. So that's the method we use there.
Reflectivity, as in like which Dr. Minalson uses.
Same, yeah, same. Right, yeah. Right.
Yes, sir. Yes, sir. Thank you, sir.
But Minal's reflectivity method is in the time domain, and Kennett's invariant embedding method is in the Fourier domain.
Okay, sir. Thank you.
Okay, what other questions? Advice on how we just need to start building up fundamentals of ML. So yeah, so like I said, look at some basic text. There are some tutorial papers that comes out in the leading edge, for example. But those are just to get started, because they don't have too much of the math. But there are also good books. You can look at, if you have no background in machine learning, then you can start learning the traditional machine learning. You don't have to dive into deep learning right away, but you can start traditional machine learning. And for that, there are many courses on Coursera, right? And those courses are free. If you don't want the certificate, I think you can just listen to those courses. So the Coursera course that I mentioned is the course by Andrew Ng. He was a professor at Stanford University. Now he has this big company. He's very famous. He's an advisor to Google and so forth, and he has his own artificial intelligence company. So Andrew Ng, Andrew Ng, right? So that's the name, and you can find his course on Coursera, Andrew Ng. So that course, definitely, that's a basic fundamentals of machine learning. It teaches you how to avoid overfitting, how to do testing, validation, training, validation, testing, how to do that. And it's a good one to get started if you have no background at all. Another question is, if one wants a career in geoscience, what should we prefer, machine learning or ferret? What was that? Typo there, I don't understand. What should we prefer, machine learning or ferret? I don't understand the question. Okay. Any other questions?
Hello, sir. I am Deepkumar Sinha. Hello,
yeah.
Sir.
Yes.
Yeah, I am Deepkumar Sinha from Department of Geophysics.
Yeah.
So I want to ask a question that can machine learning predict pore pressure for sand or limestone lithology?
It depends on your training set. Right? In machine learning, the main thing is the training set. Do you have a good training set?
Okay. So if we have any training data set, so can it follow the basic theories that in cell? How do you know that effective stress increases with the porosity linearly? Okay, and that's why the existing statistical model like Eaton equations or Bowers equations are able to predict pore pressure for cell lithology itself. But if we go for sand or limestone lithology, so and if you have a testing data set, and if you are able to predict pore pressure for sand on limestone using machine learning methods, so could it follow the basic theories?
Well, it is purely data driven, right? So machine learning doesn't have any physics. The physics is already in the training data. It is implicit in the training data. So the machine learning is just a statistical relation between the input and the output that you have in your training data. So machine learning is not going to predict the theory. If you have a good training data, it will be able to learn that relation, and then for a new data where you do not have the pore pressure, it will be able to predict. So that's all it does. It does not provide you with a it won't give you an equation or anything like that. I mean, for some models, you can actually derive, if it's just a simple multivariate regression, you will have an equation. But for deep learning models, the equation is implicit, right? But it is all statistical. It is just your training data set. If you have the training data set, the physics is in the training data set. Actually, the physics in the training data set is more than the physics that we might have, because our physics models are imperfect, right? We have approximations, so forth. But the training data set, of course, it captures all of the physics, whatever is physics, but also data always has some errors, right? It is not perfect data. So it has all the physics, but it also has some errors, and so that's also an issue.
Yes,
Sir,
sir. Got it. Thank you, sir. Thank you, sir.
Sir, I have one more question, sir. Could you please? Yes, sir. So you generated like a prior model of species, like let's say like 5,000 models, right? And then you use data and calculated the likelihood of.
Well, so far there is no data. There's no observed data, right? There is modeled geology, the facies, and there is modeled data, right? So from that facies model, we populate that with VPVS density, and then we forward similar the seismic. So now we have the facies models and the corresponding seismic data. So this is modeled. Facies models, that is geology, and we have the seismic data. So now we have a collection, 5,000 facies models and 5,000 seismic data. None of this is actual observed data, right? So this we use just to train the machine learner to learn the relation, the nonlinear relation between the facies and the seismic data. Once it has learned it, now we give it a new seismic data, the actual observed seismic data. And with this observed seismic data now, it can then predict the facies.
So, sir, there will be like if we have like 5,000 prior, so we will have like 5,000 posteriors, like in that.
No. You'll select some of them with the which are close to what you're getting, right? So the posterior might be just 30. You won't have 5,000.
Okay, sir. Thank you. I'll read.
Let's see. Is there a blackboard here? Do we have a blackboard or a whiteboard, right? So let's see if I can write there.
Yes, sir. Thank you.
Okay, so starting a whiteboard. Can you see that? Can you see the whiteboard?
Yes, sir. I'm trying to.
Are you able to see the whiteboard or not?
No, sir.
Okay, I have to share, present to the meeting. Right, so you see this, now you can see the whiteboard?
Yes, sir.
Okay, so let's say this is our prior, so it's of course in high dimensional space, but conceptually we have the prior, and now we have, let's say that these are all our models, 5,000 models, right? So we have a broad distribution of the prior. And so let's say this is our seismic data that we have created, right? So we have 5,000 geology models, and then corresponding to that, we have 5,000 seismic data. And this is a projection of that high dimensional space in some conceptual low dimensional space, let's say in some sort of PCS space or MDS space. So just conceptually, we have this 5,000 models. And then what we have is that now, so that's our prior. But now let's say that we have the data.
Yes, sir. Sorry. Are these like images? I mean,
These are representation. Yeah, each dot is a full seismic image, right? But I'm representing it in a low dimensional space. So each dot is one full representation of the geologic model as well as the corresponding seismic data, right? Each dot represents one another, right? Now we have the observed seismic data, right? So these were the priors. Now we have the observed seismic data, and we project that to the same space, and that observed seismic data falls over here. Then what we can say is, okay, with this observed seismic data, we can predict this from the CNN, and we get the facies model. And that facies model, now let's say that facies model falls over here. Now the posteriors will be just this set, which are kind of close to those observations. So now the other models in the priors, they will be rejected, right? So these models are rejected. So we reject those models because they are not close to our observation. So those are rejected from the prior. So initially we had 5,000. And now what we are left is only these models, which are maybe 50 or 30 or whatever. So that's
Yes, sir. Does that mean that we actually found out the uncertainty of our predicted solution?
Approximately, this is called approximate Bayesian computation. So yeah, approximate, because to do a rigorous uncertainty, you would either have to do Markov chain Monte Carlo or just pure rejection sampling, which will be computationally very, very costly. But yes, this is an approximate uncertainty, right?
Yes, sir. So does that mean like we use like Markov chain Monte Carlo instead of using Adam Forest like Adam optimization?
No. We always use Adam. That's it in the training part, right? That's a training part. So Markov chain Monte Carlo, we don't use Markov chain Monte Carlo. Here we do ABC, approximate Bayesian computation, which is much more numerically efficient compared to Markov chain Monte Carlo. So we could do that. Of course, if we did Markov chain Monte Carlo, then we wouldn't train a machine learner at all. Then we just do Markov chain Monte Carlo. Of course, it would take, we would not be able to find the posterior with just 5,000 samples. It would have to be 500,000 samples in the Markov chain to get to the posterior.
Yes, sir. Yes, sir. I'll read the paper for more information. Thank you for explaining.
Okay.
So how to deal with this uncertainty that arises? I mean, uncertain computations will be more in this case.
What was that? I didn't get the audio.
Sir, I was asking that in this case, sir, you will be dealing with more uncertainty. I mean, the data to.
What do you mean more uncertainty? Well, what do you mean more uncertainty? What is more uncertainty?
I mean, sir, in case some data sets they will be giving you a good sign, and you are getting the proximity that, for instance,
I can't hear you properly. Maybe you should write in the chat. I cannot hear you properly. Your audio is not coming clearly. Maybe you should write in the chat.
Sir, I have one more question, if you don't mind.
Okay.
Yes, sir. Sir, can we generate this kind of images instead of like from seismic migration or something, and like using like seismic migration, we generate this kind of image, and then if we have some data, we can apply this kind of technique to find the posterior models.
Well, I mean, yeah, you could, but your question is not clear. So you haven't defined your question properly. You need to define your question, right? Your question, you're not clear about what your question is. What do you mean? Create migration images, and then what do you want to predict?
Sir, what I want to do is like actually from the data I should be able to get like
what is your data?
My data can be like from teleseismic receiver functions or
that's a very different thing, right? What we are doing here is post-stack sizing data, right? So that's post-stack sizing data or partial stack sizing data, or near angle stack, far angle stack, or mid angle stack, right? Okay, so you have teleseismic data. So you have seismograms, right? Teleseismic seismograms.
Yes, sir.
And what do you want to predict?
Yes, sir. From teleseismic seismograms, we can generate a reflectivity image of the subsurface,
Yeah.
and then if further I have another data set, so from that I should be able to predict uh, a reflectivity image of the subsurface. Like if I
Right.
input.
So right now you say you have teleseismic data and you can predict the reflective image, right? So how do you do that? That's an inversion, right?
Yes, sir. That can be done using some by using some tomography technique. We can do, and we can find the velocity structure.
That's a conventional traditional inversion technique, right? So you do that. It's framed as an optimization problem. So you optimize. You start with some initial model, and then you optimize that based on some gradient descent, right? So yeah, you do that. So now if you have another data set, you could apply the same technique and get the reflectivity for that other data set.
Yes, sir. Yes, sir. That's what I. Yeah.
Right.
Sorry,
So now if you have one data, right? You have one teleseismic data, you can do the tomographic inversion and get the reflective image. So that's the traditional method. You have another data set, you can again apply the tomographic inversion and get the reflective image.
Yes.
That's all clear. So what is your question?
Yes, sir. My question is if I can generate like such kind of images, right, and train the CNN on those images, and then after that, if I have another data set,
Yeah, you
then
can do that. Yeah.
then
So make sure that your training set that you have to train the CNN is broad enough to capture all kind of different scenarios.
yes, sir.
Right. Let's say that you only have, say, teleseismic of. I'm not a teleseismic expert, but let's say you have teleseismic only from earthquakes coming from one particular epicenter.
Yes, sir.
And then your data set will be biased, right? You only have data for that kind of earthquake, right? You need to have data set that covers all different kind of earthquakes so that when you go to predict, it is within that training set.
Yes, sir. So I will have to I will have to take care of epicenter locations or the directivity of the earthquakes. Like from
Directivity, probably you have to also take care of what is the lithology, where the epicenter is, where it is originated. If it is originating different types of lithology or different type of tectonic environments,
like the source location and source parameters.
Source location, source parameters, directivity, like you said, all of those you have to have a broad coverage. Otherwise, if it's, let's say, only have teleseismic data coming from the east, and then you try to predict some new one that is coming from the west or north or south, maybe that will not work.
Thank you, sir. Sir, by the way, I'm pursuing PhD at Baylor University in PhD in seismology. So I'm kind of looking into these methods, and I'm planning to implement this kind of methods in my PhD.
Good, very good.
Thank you, sir.
How to deal with uncertainties? So the question from Akash: how to deal with uncertainties? Well, you have to define what are your uncertainties, and then you have to parameterize them mathematically because you want to quantify them, right? So to quantify that, so first you define what are the uncertainties, then you parameterize them, and then you create distributions for those parameters and so forth. So it's not easy, but there are some systematic ways of doing that. But that doesn't mean that you'll always be able to cover all of the different uncertainties, right? Nobody could have predicted the pandemic, for example, right? There's always the black swan events that can happen. So how to deal with uncertainties is a big question. It's almost more philosophical than geoscience. What do you believe as a revolutionary achievement of AI in geoscience? I don't know. Maybe it is something in the future. Who knows? Lots of different achievements, but how do you define revolutionary, right? What do you mean by revolutionary achievement? Okay. Any other questions?
So I think there is no other questions. It was our pleasure to have you, sir. The lecture was very interactive and will definitely serve us in a long way. Thank you for being a part of our event. And thank you
Thank you.
all the participants which are present in the meeting. And my colleagues also thank you all. And thank you all the participants in the day sessions. And now it's time to conclude the session. Thanks.
Thank you. Thank you very much.
Thank you, sir.